Okay, hi everyone. A very long time ago, well, or at least it feels like a very long time ago, I made this silly game about skiing, and seems like I forgot how to play it. It's very difficult. You have to use this QWOP buttons to control the arms and the legs, and it looks really funny. But the thing is, the way this one works is using this kind of skeleton, where you somehow shorten or lengthen those red links there. That shortening and lengthening is happening when you press these keys. So looking at this and building this, I couldn't stop thinking about this Theo Jansen's Strandbeests a long time ago. I remember seeing his these kind of things, creatures that walk on the beach there. And I remember seeing this when I was in school, so I don't know, 20 years ago, 15 years ago, something like this. And I did think about them when watching this kind of skeleton here, and I would have liked to try to replicate that kind of movement, that kind of structure that you see here. And this video is by Veritasium, and it appeared recently, like a month ago. And one part caught my attention here because apparently Mr. Jansen has used a genetic algorithm for fine-tuning these lengths of this skeleton so that it behaves in a way that walking is working well. So it's fluid, and he can make those creatures walk nicely there. And basically what I want to do today, if I'm lucky, is make a kind of a very rudimentary physics engine, so something similar to what I did here. It's just based on verlet integration. And then on top of that physics engine, I want to try to build this skeleton, maybe impose these weights and see if they really work like described on this slide. And then try to forget about these weights and try to come up with these weights with a similar kind of strategy as Theo Jansen did. So his point was to try to make this movement here be horizontal. So that would be the thing that I would try to optimize in this result. In this resulting shape that the tip of the leg is forming on the bottom. And then if I'm really lucky and I really have enough energy and brain power today, I want to also try to build a walker like this one and see if it really works, because I wouldn't need a physics engine for this part. So I wouldn't need a physics engine for this part. It would just be some constraints here and some triangles where I have to enforce some lengths, and you could calculate those like that. But once you detach this object from this wall, it needs to be able to push on the ground and remain as a solid and not collapse in some weird way. So that's why I think that I want that. And also with verlet integration, we can reduce some of the rigidity in the links. So we could simulate building this off of different materials and see if we could create such a system that still walks from with different kind of thresholds there. So anyway, it's supposed to be a kind of a fun fun project, like experimenting with these things. And I just hope I have something by the end. If I even have this thing, I'm happy. But I don't know. I have coffee and some goodies around, so maybe something will work out eventually. I'll check the chat from time to time. So hi everyone, and yeah. So this one here is just shortening and lengthening the muscles, and I don't remember exactly how, but so yeah, it looks like that. When I press O, these links here, I think, become larger, and when I press P, no, they contract, I think. So when I press O, these contract, these red ones, and when I press P, these contract, and the other one extends. So some extend, some contract. This is kind of like a piston, like if you are taking a vaccine or something, that kind of motion, like a hydraulic system. But the one here is based on rotation, and all of these are rigid. So it's quite different than what I tried to do. And I'm just curious, can this be done easily or not easily or whatever? And I built stuff from scratch, so just to play around and remember some of the math. Procedural animation. I'm not sure what you mean by that. It can mean many things. Hi Frank, long time no chat. I saw you started posting Unity videos on your other channel. In Python, I think that nowadays if you take the code that I write and you give it to AI like Claude or Copilot or ChatGPT and you tell it to port it to Python, it's going to do it. I don't think that it's a very useful thing to switch the language. I just like to use JavaScript for consistency with everything on the channel. But since we build most of the things from the bottom up, then it doesn't really matter so much. Of course, if what you're trying to do is learn Python, then that would benefit you directly. I understand that. Okay, now I also made the GitHub repository here, and it's linked in the description, so the code is going to go there. And I'm just going to start with this basic index.html file here that is empty. And I'm going to start to implement these functionalities to have the movement, the points, these kind of, usually this verlet integration is created on top of a kind of particle system, and then these segments, or some people call them sticks, impose distance constraints between the particles. So then building with these sticks different structures, you get a solid object. And that's exactly what we want, because here these are rigid. B is always going to be 41.5. And the other reason why this is important is, so verlet integration, I mean, is that it calculates the momentum, this velocity vector from the past position and the current position in some way. I hope I remember how to do it. If not, I can check the code from my previous project. And that's important because if something happens between the past and the previous and the current position, like the current position is bumped up by something like the ground, then the new update is going to be taken into consideration for the next update. So yeah, hopefully this becomes clear in the end how it's going to go. Yeah, and I hope I remember how to do this, because it's been many years since I've done something like this, I think. Or I'm not sure. Maybe a year or so. So let's see how it goes. And okay, chilling after a lengthy exam sounds great. So let's start with just basic stuff. Also have a different computer now, and I'm not so used to the keyboard, so that's going to be fun. So title, let's say something like this. And I'm going to use canvas in the body. To draw and animate the things on. And let's just go with these sizes and give it also a way to know where it is and how big it is. So I'm going to do the background of this canvas, or maybe the border. Let's make it 1 pixel and black. So this would be now the space that I'm working with. I think I want to have a kind of a horizontal view this time. So I'm going to go here and change the width to maybe new keyboard 900, 1000. This is fine. And the height, I think this is a little too much, maybe 500, because I want to put I want to put the developer tools. Oh no, what did I do? The developer tools at the bottom this time, like this, and this is going to be the active region, so to speak. Let's align it also a little bit better to center. Like that. Okay. So this is where all the magic is hopefully going to happen. Yeah, I'm listening to music. I don't want to take this too seriously, but at some point I might have to turn it off if I can't concentrate. So let's see. Yeah. So particle system. I'm gonna need some way to define some particles. And let's try to figure out how the structure for those is going to look like. So maybe, let's say I define here a particle like this, and it's going to have a xy coordinate. I think all of them will be like this point particles. I don't want to worry about masses or sizes. They are just like infinitely small things there that are used to define segments between them. So really the only thing I want to define here is x and y, and I think I'm just going to do it like so. But that's fine. And then let's have a reference to the canvas's context. So like that. And I want to be able to tell the particle to draw itself on this context. So at least these two things, the constructor of the particle has to look like that, and the drawing method, I want to draw this particle on a canvas of choice. If we do some experiments with multiple structures at the same time, maybe this genetic algorithm, then being able to draw things on different canvases might be eventually useful. Or we can use the same canvas but change the offset. We'll see. Anyway, so this is something that I want to work with, and this particle, I'm going to initialize it in its own class. So let's create its own file here, and X, Y, and I don't know why radius is mentioned there. I don't have such a thing here. And now I'm thinking that maybe I want to already start working with vectors. So perhaps grouping this as the location of where we want this particle to create. So this location will have an X and Y. Maybe things will work better in this way. And maybe the vector class, okay, this AI is figuring out what I'm trying to do. So vectors will be implemented there. And here we just store the location. So this location like so, and draw on the CTX. I think we just do a small dot at that location. So let's have the radius as a parameter. Maybe we want to control that in some way. And black is just fine for now, at least. Maybe later we need to emphasize them differently depending on what kind of particles they are, but I don't know. Okay, so something like this should be fine. Vector is not yet needed, and I don't know if I want to use vector objects like everywhere, or if these JavaScript objects are enough. I tend to like a simpler syntax here and just making the operations as global functions, because the syntax is somehow easier to write. You don't have to type so lengthy function names. What I would really like to do always here is do some operator overloading for the vectors, but JavaScript doesn't support that, so I'm somehow stuck with it. Anyway, once we have more code, refactoring a certain way or another can be done then. Now it's a little bit too early to think about that, I think. I'm really not sure what all things we need. At least these segments here, sure, but then this one here is a special kind of particle that doesn't move. And then this rotates in some way, so this is kind of like an engine here. We see later about what kind of code structure is the best. But for now, let's just keep things simple. And I think that this one works. So the particle is there. And I could define more of them, probably. Let's try that. So in an array, let's say 50 of them. And now I'm going to, do that. And after that, I'm gonna loop through them. And draw all of them. So now refreshing gives us this kind of dots on the screen. And that's fine. Now, these dots should be affected by some kind of external forces. So for example, gravity could be something that affects them. And figuring out how to do that, maybe I'm going to try to look at these past codes, what I did here with this one, because I think that it's going to speed up some things a little bit. And okay, good. So this location was grouped together, this xy. The old one is also initialized for some reason. So the particle keeps track of where it was and where it's going, where it is right now. And here, when you update, depending on whatever forces, you calculate the velocity from the old location to the location, and then you add this velocity to create the new location from the current one. Yeah, this kind of makes sense. And then you update old location to the current location and the current one to this new one that you need to calculate. This makes sense. So the forces here, I think I considered maybe wind or something. I don't know why I wrote it like this, but gravity is basically the only force that will bother us. And let's have one of these update according to this gravity. So I'm going to define this gravity force as, let's just keep this object for now. I don't know if we need this vector object as such, but increasing on y. So y is 0, 0 in the top left, is 0 at the top of the screen. The top left corner of the screen is 0, 0. And it increases downwards. So this is the same way that I want the gravity to affect. And with this, I want the particles to update in some way. So let's try to figure out how to do that. Old location is set to the same location in the beginning because the particle is assumed to be stopped. So it hasn't moved from the previous update. And now when we update, this is just some force here. It could be gravity or something else. We could have also multiple forces, like in that Master Skier game that I had previously. But I think that one force is enough for this, and I don't see the point of over-engineering some code that won't need that. It just becomes more tricky to understand what you did there when looking at the simple prototype code base. So now the velocity. Yeah, that's what I want to do. I want to subtract from the old location the new one. But this assumes that these locations are objects that have this kind of sub method. So we don't have. And I think I want to go with this one as we had in the previous code base. Let's not. Let's be more proper so that I don't teach some bad practices. So the particle comes from a new vector object. Let's go here in the vector file and say like that. And like so. And this method subtract that Copilot wanted to write here is just like that. So now when we go here, we have to pay special attention that the particle is going to be based on a vector. And I could write here new vector with those, but code just becomes too much. So I prefer to keep it here simpler like this. And this line becomes a one-liner. We are creating a particle based on this vector and then adding it to this array. This is much clearer, I think. Okay, and then what did we have here? we can now do this subtraction there because the method is available there. And this should also work because the vector does have the xy properties. So this is all good here. And we can continue with the mathematics. So we have the velocity. This wants me to update the old location to the new one, to the current one. It's fine, we can do that now. And then to add the velocity and also add the force. Yeah, this could work. And the code is quite okay. We are just missing this add function here. So same thing here, but with a plus. And now this should work. So by work means it doesn't do much, but it shouldn't give an error, I think. I'm wrong. There's some error. Oh, here yeah. I don't know why it's doing that. This vector is not a vector. So now it needs to be used everywhere. So we have to be careful about that. And it's not the only reason. So where is this breaking in this here? Let's go and type debugger here. And this is going to stop the code there. It doesn't reach there. Oh, they are undefined for some reason. A vector of particles is object. Oh, actually this is probably the problem. The array of particles can be like that. It doesn't need to be a vector. We don't have multi-dimensional vectors here. But this works. Where are the particles? So particles, many particles, undefined. Oh, yeah, this code here doesn't need those things. So X was a combined object of X and Y. Now it works. And if I'm going to run this code again and again in the console here, you can see those particles start to drop. They leave the line like that because I should actually also clear the canvas before putting this code. But now if I run this multiple times, you can see the particles start to move downwards on each iteration, and actually they speed up. So the reason why they speed up is that on each frame here, the velocity is calculated from the old location to the new location. So that's an amount. And then to that, we add those forces, that one force, the gravity. Now, in the next step, the old location is here, and the new location is the one at the bottom. So it's bigger. It's bigger than what we had previously. And to this bigger one, we add again the gravity, and it becomes a new, even bigger one. So basically, the speed increases. It's not a constant speed anymore. And this is just fine. So if we run here an animation loop, like this, putting this code there and also this clearing of the canvas beforehand, then you see them going down like that with one problem. Yeah, inverse kinematics, that's also something that could be used here. That would work differently. So the idea for that would be that you first draw this curve in some way and then make the other components of the skeleton move in a way that the tip is always going to be on that curve. But the problem with that is that it's doing it by changing sizes of these typically. So that kind of a piston-based approach. And here, this shape, this movement is made from this circular rotation there. So this circle here is the only thing that is powering this. So it's not really possible, at least I don't think it's possible. I'm not an expert with that technique. But this circle is quite limiting. So finding these, and the fact that these are rigid, so these can't change in size. They are always fixed to the same sizes that appear listed here on the left. So those are limitations that don't let you decide first where you want the tip to be and then change properties, because the only property that you can change is this angle around this circle. Everything is fixed in size. Okay, let me check quickly the chat. So, okay, Daniel, salut! Mă bucur că ai învățat chestii. Da, cu plăcere. Și yeah, vector parameters should not be object. I think you wrote that as soon as I saw the problem. Yeah, but let's try to enforce a little bit the code structure this time, and maybe in this way we don't forget something like that. Okay, nice. So, where were we? These go down. I want them to stop somewhere. So I want to constrain the particles somewhere. So particle constrain. Yeah, we can do that. So it can't fall underneath the canvas. It can't go to the right of the canvas or to the left. Left is 0, top is 0. So I just need to put two variables there, two parameters there. So constrain, and then no, right and bottom, or width and height might be also nice. But anyway, this is fine. The only problem I have with this is that I'm not sure if I want the old location to update in this way. And also, if I do want it to update in this way, I don't need to duplicate these lines here, because you can just type here old location is equal to this location after you do the change. And this is going to be doing the same thing, but the code is smaller, is shorter. Yeah. And now, if you want shorter code, you could get it like this. So X is going to be the minimum between this location X and right. So this line of code here is the same as this one. Think about it. If this X is greater than right, it becomes right, or X becomes the minimum of whatever X is and right. So if it's greater than right, it just becomes right because right is smaller than whatever the value is going to be. Some people like writing it like this, but it's basically the same thing written in a one-liner. And if you want to be more extreme, some people like to do here max between 0 and min of the other one. And this is going to also handle this if, because when you get negative values less than 0, 0 is going to be the maximum, so it defaults to that. And basically, this thing, what we have here in one line, is the same as this. And some people who are used to this prefer it because everything becomes much shorter. And now I'm just going to keep both of these. Just for educational purposes. So when you study the code, you can check the differences. But they should work. So now if I'm going to refresh this, for some reason, it doesn't work. Okay. This doesn't work as expected. So this old location here doesn't need to be set to that one. Maybe at all, let's say. Because if we do that, then we negate what happens in the update. So old location becomes the previous location, but then we update it to be location after this constraint, and it negates what we just did in this one, because the difference between the old and the current location is what's gonna set how much it moves in the future. Yeah. Yeah, if you take out that to a clamp function, it will improve readability. Yeah, so Baruch mentions even better. So this, you can add a comment there to make it cleaner. This, you can also add a comment to make it not cleaner, but clearer. But if you take these into a function called clamp, and you give the parameters like the lower and the upper value, then that makes it even more cleaner. So no matter which one you take to another one, it's going to make this code be just 2 lines of code. And this already makes it a line, and the other could be made in the same way. But the point that Baruch is making is that this is confusing. It's not sure what it does. And clamp typically means that you keep things within a fixed range. If you know that term, then using it is going to be very clear what happens in that part of the code. I'm going to stop improving code quality now. I think this, yeah, okay, I'm getting it there. Let's copy it from the chat. So maybe I'm going to make another file called utils. And add here Baruch's function there. And with this clamp, I can force everything to be, let's use it now for the y value. So yeah, this should work. And I also have to include this file here. So refreshing error. I'm including it somewhere. Oh, okay, tricky one. There is some weird character coming from the YouTube chat, I think. Very weird. Yeah, still works. So thanks. And moving on. So no need to do the pedagogical thing anymore. Let's just do it. So right. And this is fine. So what we next need to do is also impose a way that given particles don't get closer or further away from each other. I'm going to work with this kind of a system here, with these random particles for now, and generate segments on top of these particles, those kind of rigid things. Let's call them sticks. So two particles are going to form a stick. I've seen some people calling them sticks in their implementation, and when I think of stick, it either breaks or it doesn't. So it doesn't extend or change size. Maybe it makes sense to call it like that. So let's say sticks. I want to pair them somehow, like maybe every two. So let's say I plus equals to 2 here, and this is fine. So the sticks are going to be made out of a particle and the next particle, and then we skip that, and we have the third and the fourth and the fifth and the sixth, and that's okay for this demo purpose. And to test what we have here. Now these sticks need to be implemented somewhere, but after they are, I want to be able to update them as well, like this. And the update doesn't necessarily care about gravity anymore. Because it's already affecting the particles themselves. This constraint is something that I feel should come afterwards, because we will do something with these sticks to make sure that they keep the same distance from each other. Yeah. Okay. So probably this needs to go down. But now these update, and after they update, we can also draw them in the same way that we do these particles there. I do it before the particles because I want to see the particle on top of the stick. We'll use different colors. So the next thing has to be in this file. So P1, P2, I don't know why a third parameter would be needed at this stage. Maybe it's a good idea later, let's see. But at the moment, I think that this is just okay. And we store these particles. And yeah, so this is important here. The distance between P1 and P2 is going to be the length of this stick. And it seems to be calculated like that. We need a function for that somewhere. Distance is not really a function that you would add to a method that you would add to the vector object. I mean, you could do something like subtracting one from the other, and then to the result you do the magnitude. Yeah, that would be something that gives you the distance. But then this is kind of, I prefer to take a distance function elsewhere because it's just more clear as a thing between the points, and now the vectors are represented as xy offsets from the 0, 0 point. So this is fine. We can write it with this other function, maybe better. Okay, so now inside of the stick, we could just say here the distance between P1 location, P2 location. This is one way that we could do. Or probably even better is to add the distance function to the particle itself, a distance method. So like this to another particle, and then return that, because in this case you don't need to know at this level that the P1 particle has a location attribute. So you leave that to the responsibility of the particle object, and that can make this level of the code much clearer. And we are still using the distance function from here, like that. Okay, so that's the length. Let's have an update function, and I'm just going to leave it empty for now. I like to debug as frequently as possible. So yeah, this is fine, but let's put also a color, maybe red, like this. And let's make it a little bit thicker. And now you see what kind of happens. It's It's kind of messy. I think I'm going to switch to having very few sticks because it makes things easier to look at. Maybe 6 particles, which means 3 sticks. And notice what happens to the ones that are vertical, like this one. So try to look for the vertical sticks, like this, and see that the points become closer to each other because we don't enforce them to stay the initial distance. Let's put just 2 particles here. And no. So now I'm forcing them to be kind of one on top of each other almost. And you can see how the segment becomes very small there, this stick, and it shouldn't deform. So that's the next thing I want to do. I want to keep the length from shortening as the top particle gets closer to the second one. I don't think I know this term kinematics very well. So I have a basic idea of what it means. It means that try to figure out the tip position or to figure out the other distances depending on where you want the tip to be, if it's inverse or not. I really don't know well this term, but I don't think it applies here because all of these are rigid. And the only control you have is this circular motion here. But maybe the fact that we do this, that we will try to create this structure and optimize it to have this kind of path, maybe that optimization step could be considered as 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 kinematics. I don't know. And if somebody wants to explain things better in the chat, then that would be good. Oh, okay. So it's more than what I thought. Yeah, okay. But inverse, I think it means what I said previously. So this end effector, I think it means, so you have forward kinematics and inverse kinematics. And I think that in the inverse, the position of this end effector is known, and then you control the other things somehow. Like in this case, the angles. But I guess you can also control the lengths of these things instead, if they extend. But here, the lengths and also the angles in some cases, like here, these angles are rigid. They form a triangle, and this triangle doesn't change its angles at all. The only thing that changes angle is apparently this quadrilateral there, and also this quadrilateral here, because they don't have some kind of diagonal thing there. But they change it in a way that it's imposed by this thing. So, yeah. I have to look up these terms better and see, could you use some other approach to this? But now my only issue is this. So I want this segment to stay a certain size, even if it wants to deform in some way. So you can do that in several different ways. Like, let's see, can I draw with this thing? Like if you have your, okay, no, I don't have. Okay, and let's say that this is P1. Oh, I don't want these fields to be here. How do I remove the field? Is it even possible anymore? I don't remember with our drawing app. So I think that we can't do it anymore, but maybe, okay, that's the hue. We can make things transparent at least. So let's make things transparent there. And so this is now P2. And let's say that the length that it should be is this one. So this is the length that was created when we initialized the stick here. And this difference between P2 and P1, like this, this vector here, of course, if you think that this would be here somewhere 0, 0, then the difference vector between those is going to be either this or the other one, depending on which orientation you choose. But we can calculate this difference somehow, this difference vector. And now this difference vector has to be scaled so that it has the same magnitude as this length that we calculated previously. So normally the way you do that is you take the vector and you normalize. So after you calculate that difference, from this 0, 0, you just maintain the angle. And then this new length here is going to be 1. So that's what normalizing usually means in terms of vectors. And this one length vector, you can just scale it by this length. So you multiply it by this length there. This is kind of the one approach that you can do. But you can do many other of them as well. Like you can take this difference and you can subtract the length. So then you get this plus this. From that you can divide by 2 and you get only that. And this you can move P1 with that amount in this direction, and then P2 you can move it in the other direction with the same amount. So it's either one way or another. I'm not sure which is more efficient implementing it. But I think that the first one I described is simpler. Normally there are many different ways to solve the same problems in practice. So let's try the thing with the difference. We need to calculate the difference between P1 and P2 at the current moment. So the difference, let's just use the same 1f here as in the drawing, is P1, the location of P1, and we subtract P2. And now with this difference, I want to be able to normalize this vector. So then like that, but this function doesn't exist yet. So this is going to give us this one right here that preserves the same orientation but has a magnitude of 1. And then this one needs to be scaled by the length. But that doesn't really help us so much here. We really need to move P1 and P2 in this direction and the other direction, after all. So yeah, so maybe... Or you could calculate the middle point here, the average point, and then move half the length in this way and half the length in that way. Yeah, there are many ways of doing it. I don't know. I think that I'm not using TypeScript because I don't want to install more things than necessary, and I think that these modules are... sometimes I end up in some class where I don't have VS Code installed or whatever, and I need to do some quick modification to some code and run it, and I should have this live server enabled, or set up some local server, but I don't have the tool for it. And very often I can just do the editing in Notepad or whatever is installed in that room. So it's just convenience for me. Don't do what I do. I have my reasons, and they are not normal reasons, because yeah. Okay. So let's move to from the center point. So average is going to be P1 location, P2 location. So that's going to be the center point. And now this the scaled vector is going to be, I want to go with norm scaled by this length divided by 2. And now P1 location is going to be average added with the scaled one, and P2 we subtract this scaled one. So one of them, from here P1 goes that way and P2 goes that way from this center point. And we need a lot of things here. So we need scaling, normalizing, and the average function. So in utils, I'm going to go like that, and that seems okay. And in the vector, scale is... the parameter here is not a vector anymore, so it doesn't have x or y. It's just a number like this. And normalize is where we divide by the magnitude. So we divide by the length of the vector. This is correct, but magnitude doesn't exist. So the magnitude is like that. Or you can use the distance function, but actually this is quite okay as such, because you don't need distance between it and 0. 0 is 0, it doesn't offset anything, so you can just type hypot with x and y respectively. And this might work. Let's try it out. Errors. P1 is not defined. So in the stick implementation, this P1 and this P2 is needed everywhere where we are working with P1 and P2. Yeah, okay. Okay, so this is something. They slide, so some kind of friction will be needed. If not, eventually when the thing is gonna move, uh, it's just gonna like ice skate in place, so not something that I want to do. Okay. Soon I have a feeling we will need to make this code here better because it's becoming very messy. But I think that now we have these things. It's time to try to define this structure already, I think. This thing. So I'm gonna do something a little bit weird. And I'm just going to eyeball this shape. So I want a particle here and a particle here and one here. These are vertical in the beginning. I'm not going to calculate these distances very carefully. I will just eyeball them and then force them to be some specific number according to these values here, if that makes sense. You'll see. I think this will work. And one particle, I think this one, red one, needs to be static. No, not the red one. This one here needs to be static. Wait, this one also. Both of them need to be static. So this is like a center point. This is a rigid arm here that moves in a certain way, but this is also a static bit, like bolted into this structure here. You can think about this as the wall. Like here, you can see he is demonstrating it like that. So so the point here is this one. His hand is here. There's another point, but it's not here. Okay, there's another point. It's not there, but this seems bolted. See? So what this point might do is the same as bolting that one there, I think. And it's up to us which version we implement. I think that the reason this is proposed here is because when you have this crazy thing, bolting them here maybe makes everything easier to assemble. Like I'm not sure. Yeah, connecting to body. It's very hard to tell what is happening because this thing is so complex. But let's try both. So we have numbers here for all of these, and I'm just going to make static 2 points, 2 particles here. I would also like to label these somehow. So, mhm. Okay, I think this seems to work. So I would like to also label these things. Let's change the color with to something that goes with this blue here. Okay. Yeah, I think this is fine. And I'm going to use upper letters. So let's say that this thing here, this is one of the most important points. So I'm going to start with that one and say that one is A, and then this one is B. C, D, E, F, G, H, I. Now, no, better idea. Let's undo a lot here and use numbers instead. I mean, I am using uppercase, but starting at 0 and going like this, it's going to match to array indices. So let's just do this instead. And in this way, we make it less likely to have. Okay, let's try 2 here. And then 3, 4. Okay, 3, 4, 5. Less likely to make mistakes because it's very easy to start confusing letters when they repeat, even if you have different versions. Yeah, we don't need the red one to get it working. We could put this one. I don't know. I don't know. It's hard for me to see. Maybe you're right. Yeah, the red dot is the connection to the rest of the skeleton. But this is fixed. Like there is an imaginary triangle here, this right angle triangle that is really fixed in some way. So let's see. And if this is attached to the rest of the thing, maybe it would make sense to move this one to be wait. I don't know how they were anymore, but maybe it makes sense that to be the 0 point. since taking the 0 point, overthinking. Both of them are important, so I feel like the center of this circle needs to be the 0 point. And let's try to define these. So instead of having these random particles here, I'm going to say particles push new particle. And let's just put 400, 400. So this will be this 0, and then 1 is going to be a little bit lower than that. So 500. It's a lot lower, but anyway. And upper, higher. So let's say 200 and 210. Let's see how this goes. Okay, and they are falling 220. So, and they are falling. These need to be static somehow. So I'm going to add another parameter to this. And here is static. It's by default false. But I can force it to be true. And in that case, if this is static, we don't do anything. But also the stick here, it shouldn't update that particle if it's static. So if it's not static, then we can do this thing. And if this one is not static, we can do that thing. It doesn't work. Yeah, it shouldn't be in the vector. It should be outside the vector. Okay. Yeah, you fixed 2 points, but I think somebody pointed out, you pointed out previously that, or no, Baruch pointed out previously that you needed to somehow yeah, it pointed out that you if we eventually make more of these legs, we probably need that that other point as well. Let's see. And yeah, I do want to have some genetic implementation today. Let's see how my brain works. It's already after classes, so I can't do very long coding sessions these days. But this is such an interesting project that I might try. Okay, so we have 2 of them. Now the third one, where was it? So index 2. This is something that we will need to think about how it can be having a fixed length to this one, but it will spin according to some clear rule. Let's see. At the moment, I don't care. I just want to create the structure that resembles this. So it's even higher up. And I'm just going to eyeball things here. So the third particle is going to be 170 here. And this is not going to be true. So this one is giving an error. Because these sticks are trying to be added there. No sticks for now. Okay, so that point is there, but it just falls. And maybe it's a good idea to start to define the sticks as well. So we have the stick between 0 and 1, and the stick between 0 and 2 at this stage. So I'm going to name them I want to name them like here, like in this like in this video, ML, because they have values here on the left that I try to use at some point, or we try to optimize in some way. So L, I don't like L because it looks like I, but yeah. So between 0 and 1, we have L. New stick between 0 and 1. Okay. Then between 0 and 2, we have M. Between 0 and 2. And we can just push these. So sticks is going to be L, M, and so on. So now when I go here, they are appearing there. And I can go on with the next one. So next one is 3 here. I'm just going to eyeball it to the left and a little bit to the top. So maybe something like this. And this is going to be between 2 and 3, and it's going to be called J. So between 2 and 3, and J is there. Okay, something is okay. Now 4 here, it's same height as 1 and a little bit to the right. So let's copy this one, remove the true, and a little bit to the right from this one. So 3, 2. Okay, and connects to 3 and to 1. 2 connections so far. So to 3 is B and to 1 is A. So B, 3 to 4, okay. A is 4 to 1, not to 0. And let's put here AB like that. And refresh. Okay, we have something that looks like a start. And now 5 here. So even lower. I'm going to put here these indices so that I can read them easier. Okay, and this was lower, like 270, and a little bit to the right as well, maybe 330. And it connects with 2 and with 4 so far. 2 and 4, so K and C. With 2 and C, it's with 2 and 5 and 4. Yeah, K and C. So C, K, okay. What do we have now? Something is not right. I connected it to the wrong one, didn't I? Oh no, it's good. Yeah. Now this angle here looks bigger than the one that I'm making, but I don't care. I don't want them to be so precise because I will enforce them to have certain sizes at some point. This is just a way to make sure that I'm adding them and that I'm adding the correct connections between them. Yeah. And I also think that these need to be fixed somehow. And if this one is, if I fix this one, this number 4, that's one thing. Or I could add another link here. So there's something missing in this drawing, really. Another length here. But anyway, we did 5, and now let's do 6. So new particle much more to the left. So let's try 250 and a little bit lower than 4. So let's try 220. And it connects to 3 and to 4 so far. So notice I'm only connecting backwards. So E to 3. So 6 to 3. And D is 6 to 4. 6 to 4. And let's put D and E here. Okay, and now 7, lower, much lower, and kind of in between 6 and 4. So let's say 270, and between 6 and 4 on the X is something like 28, maybe. Something like that. And 7 is linked to 5 and 6. So G and F in this case. G is 5 and 7. And F is 7 and 6. 7 and 6. F and G. Let's try refresh. This seems okay. And 8, I think, is the last one. So 8 is quite between 5 and 1 horizontally and quite low. So between 5 and 1, so 5 horizontally 330 and 1 is 400, so maybe something like this, and lower than everything else, maybe 310, something like this. And this connects with 5 with I. So 5 and 8. And H is 8 and 7. Okay. And this looks like the alphabet now. That's fine. And now if I refresh this, it's the whole structure there. But really, one thing here, that one thing would need to be stuck as well. So let's stick it for now and then later see if we need another thing here. But for the fourth index, I'm going to make static. So like this. And now if I'm going to refresh this, something happens, okay? Something happens because gravity starts to move things around. Yeah, gravity starts to move things around. And I think also because some of these segments try to be rigid, but they are not exactly rigid. We'll figure that out soon. But now let's have a break, and I'm going to add here the same lengths first. So let's try to add the exact same values from here to see how those look like. And yeah, let's see. I don't know what to advise about mathematics. I mean, mathematics is so big that for this specifically, I think that linear algebra is what we need, but you can always do a small modifications. You can always diverge a little bit from this project, and then you start needing all kind of things like calculus or. Yeah, maybe we could use polar coordinates instead. It seems like I'm doing that. I mean, when I was defining these coordinates, I was saying looks like that is this much relative to that and that. I was not really switching to polar coordinates. I wasn't measuring angles. But what I was doing, I was changing the 0 point. So when I was talking and saying this is halfway between this and that, I was kind of imagining maybe relative to this new 0 point that it's halfway towards the right when calculating 5. So maybe doing things relative to the others would make sense. But what I want to do now is something a little bit hacky. And the previous thing, what we did here, it didn't need to be perfect. I just wanted to get the correct connections between these nodes, between these particles. And now I'm going to force A to have a length of 38, for example. Yeah, Adita has a good answer there. Make 3 static, it should freeze the whole thing. 3 static. Yeah, it does. But I don't necessarily care about it being static. Good to know that it does that, though. One is just an origin point. Okay. Yeah, so I don't need to refresh. Sure. It's a good point. I could also disable the animation loop. Like if I do this, then I think that I see just the first frame. I don't know. Anyway, my music ended, so I have to do something about that. And next, I want to try to hack the lengths to be a specific size. Yeah, let's see. So I want this L to be now. I don't like that we are using. Okay, so L in this slide is a length, and now L in my code is a segment. Oh, I think I want to rename these with S underscore in front for stick segment, whatever. And then same for these ones here. And the stick is going to have an enforced value here, L and M and J and B and A, K, C, E, D, G, F, I, and H. And now those L is equal to 38.0. Wait, these are in order, so let's just do that. A is 38.0, so A. B is 41.5. C is 39.3. D is 40.1. $55.8. So eventually, if we get to do the experiment, these would be values that we hope to find, not knowing them. G. Why is G not here? It's here. I hope these are correct. Let's put 36.7. I'm having a little bit I'm a bit worried. It seems strange that the numbers go like this and then this on the last line, doesn't it? $61.9. Oh, 7.8. M is 15.0. Okay, and now these sticks don't really seem to need to be defined separately anymore. We can just add them here. Let's see. But now, when the stick is defined with the given length, by default it's null, and then you have to calculate it. But otherwise, we just use it like this. And I think this might actually do the trick. So refresh, and everything is broken. Let's see what happens if we don't do that. Okay, so this still worked. But otherwise, with the given length there, okay. These static points, they should move, really, when they are being initialized. I'm going to remove this thing for now, just to see if it works. And remove that animation just to see the first frame. Okay, so I have this thing. Hmm. Okay. Okay. This is not easy. Let's eliminate gravity for a while. And then things just collapse on each other, on themselves. Let's put this 0 point static. Okay. Yeah, I think the problem is these lengths that we have here are maybe a little different than the other ones, too different. And then it starts some kind of a chain reaction. Like some of the sticks are adjusting and breaking the others and so on. I was hoping that I can initialize this without big problems. What is the result after this stabilizes? So let's see, does it stabilize to something decent or no? No, this looks very bad. Hmm. Yeah. Oh, okay. Somebody from Romania. Yeah, thanks. Not using multi-line editing. Uh, yeah, I think I didn't use it because these letters were different on each line. Can you use that in a better way? Maybe, I don't know. Oh, does it really? Does it suggest the right things for multi-line? Doesn't seem so. It doesn't seem like it works, at least not in my case here. Grouped definitions, yeah, that would, that does, but do they then, they don't align next to each other, do they? If I put the, okay, they align somewhat, okay. Yeah, okay, I can do that. Oh, okay. Something like this. For slow motion, yeah, I could do that. You think that it reveals something that we are not seeing, probably. Yeah. Let's. I want to debug in a way that is not visual. So, like this. I just want to see on the first frame here, what are the values that so SA is 38. Where is it? Is it this one? Okay, maybe 1, 2, 3, 4, 5. Yeah, I think that what I want to do now is actually arrange these ones in order, and also it's otherwise it's like a chance for errors to appear. I needed them in different order when I was defining the structure. Okay, and actually I think that I can just do this. I don't think I need those named values there, because the name of the stick is going to be also obvious from this last line there. So maybe we just do this. And then that, and then that, and then that. Something like that. Mm. Okay, I get the points. Oh, okay. Good to know about these issues. Yeah, thanks. I have to freeze before the update, otherwise things are not clear. Sure. But now, 38, 82, 72, 70. It seems like in my initial drawing, things were almost double. I know what I'm gonna do. Hi, Peter. I know what I'm gonna do. I'm gonna hack this thing so much. Um, Desired length is that. Now this length is going to be that. But when updating, I'm gonna get closer towards the desired length by some amount. Like, okay, let's leave like that. And this is just an experiment. I don't know if it's gonna work well, but something like this. And then and then it doesn't work. What happened? Doesn't work. Oh, it's still moving. This kind of looks okay now. This looks okay. Okay, so um, I'm gonna do it like this. I fixed the first one. I need these to be fixed in the beginning. So L and A need to be taken into consideration when building it here. So L is between 0 and 1. L is between 0 and 1, and L needs to be 7.8. So basically, plus L here. And 0 and 1, they 1 is also static, like this. And now 4, so the fourth particle here, a distance away, it's going to have 200 there, but this one is going to be 400 minus a, and also fixed. And now, yeah, I think it works. I think it slowly became this. So this one here and this one here. I think it's good, but this dot here at the top, it doesn't go in a straight line because it's not yet made to be an engine, a motor. So basically it goes like that. It tilts to one side because everything else is pulling it there. But okay, I think that this is fine. Okay. Point 1 is not there. It's an imaginary point. Okay. Yeah, you're right. And I also seem to have it wrong. It's relative to this position. But I think that there's no problem having an imaginary point there. Okay. Yeah, crazy. Yeah, doubling should have also worked. But now I decided to go on this idea that they gradually change so that the structure doesn't get distorted much. There is no stick between one and the one above it. This one. You mean this one here? But they seem to be, I mean, these seem to always be in this fixed configuration, as if there is also a stick here between these, but I can see from this one that you are right. It's just, yeah, okay. Okay. So you mean that this point has to be fixed. And this is just unnecessary if both of these are fixed, like in this animation, like in this configuration here. Yeah, I can see that. But I don't think that keeping it there is going to break anything, at least now. It could simplify it later on. So good to look at that later if needed. No sticks involved with point one. Yeah, no sticks involved with point one. Point one wouldn't need to exist if these are anchored to something. Okay, sure. Let's remember that. Okay, so you tried this. um, yeah, this point is static at the moment. And yeah, you could definitely use polar coordinates for everything here. So these sticks cannot be there. These sticks, L and A, you think that they shouldn't be there, that you only need them to know the offset from this one like this and like this to be able to define them. But you think that removing those sticks changes something, really? Let's try. So now they are like that. But if I remove them, so which one were they? It was L and A. So the stick for A and the stick for L. Yeah, I think it's not really a difference at the moment, but later when moving the structure, you could be right. Let's see. I'm going to move on to the between 0 and 4. Yeah. Yeah, between 0 and 4 for yeah, and I think we actually see this in, or we don't see it here, but this part in the middle seems to be very rigid. Actually, this animation here, this structure here seems to have those sticks. Yeah, I just leave them for now and move on to implement some kind of motor. So maybe I go here, and then after the motor is there and it starts to move those things, I refactor this so that they are components of lig object or something. So I want to clean up the code a little bit because it's already kind of messy. Let's just see what happens when this motor starts to move. So the motor, I want it to be new motor, particle of 0 and particle of 2. So particles of 0 would be the actually I disabled gravity, didn't I? Yeah, I disabled gravity at some point. Good to remember that. Particle 0, and then that stick, I could give the whole stick maybe, this M stick. So the last stick, basically. Or just particle 2. I think this is just fine. And origin and tip, something like this. And something like that. So I want the angle from the tip to the origin. And now this is like angular speed. And the new tip position relative to the origin and that length. But this is attribute when defining it. All of these are. Okay. It doesn't work. Oh, maybe these should have getters and setters for the location. Let's see. Okay. Oh, Okay. Well, that part is okay. Okay. Sorry, I'm checking now the messages. Mm-hmm. Okay. Yeah, there's no gravity at the moment. Now there is. Okay. So I think that this motor might be needed twice. And the update that the sticks are getting might need to be repeated multiple times as well, because it makes the segments more rigid. Is this really so long? I think this is too long. Why is this so long? Zero and two should be M, and M should be 15. Okay. Zero and two. Yeah, okay. Um, they are static, so they don't change. But wait, it was supposed to be defined that position. I have some mistake here. So 0, 1, and 4 points were there. So 0, 1, and 4. But 2 also needs to be in the correct position above with M. So 2 is here, and it needs to be 0.0 minus M, basically. So 200 minus M. . And I think I need to mark this point as static, because otherwise it's being adjusted by the other forces. Okay. I think it's working. More torque. Let's see if we can use just one motor here. So I think that it can be just before the segment updates. And it's still going to work now when we got these other things right. So in the beginning, there is this time when I didn't want to bother with the coordinates, and it's like this kind of adjustment phase. It takes a while for the errors to go down to 0. So if I'm going to plot here the error that the sticks lengths have on each frame, so I could go here and say error let's do that. So I want to calculate the error that the sticks have relative to what size they should have. Error. And now I guess absolute value is okay. Many people typically square the errors, and normally it's okay. But I mean, here, this is what happens. So the error is going down, and at some point the error becomes very small, almost 0. And this is reflecting now the exact configuration that we want to have according to those values. But the question is, can we do this faster, or does it break something? I think that now when we have all the sizes proper, all the dimensions in place, these fixed ones, this is not so critical anymore. Or I'm wrong. So yeah, it still will take a while for it to consolidate into these values. But once it does, it seems like it's moving according to that curve. We have to visualize it to say. Yeah, we need to show the leg's trajectory. So let's do that. And also account for that weird moment when the system stabilizes in the middle. So we can start recording the trajectory when the error is below a threshold. So, okay. First of all, a little bit of cleanup. So let's make a leg object. And this leg is going to be defined at some specific location. And I think that I'm going to choose now this 0 point for the location. So new leg at 400, 200. And actually, yeah, all these parameters here are important for it. Okay. And these kind of codes, they go inside this leg object. So X and Y, and then A, B, C, D, E, G, H, I, J, K, L, M. Was the M the last one, I think? Yeah. Okay. And now taking these next to this origin, and those. And now the particles, I'm just going to push this origin. So this origin vector goes here. And now here I could use those additions. So origin vector, add 0 on the X, but L on the like that. So relative to this origin needs to be there. And then this one here, sub M. And this origin was 400, 200. So now I actually would prefer to have everything relative to this. So originally it was 400, 200. And now this difference is going to be, let's just keep add everywhere. And I think that this makes things easier to not make a mistake. So 300, 130, this means minus 100 and 70. Minus 70. And then here, minus A and plus L. Or just L there. And then this one, Okay, minus 70 and plus 70. So this is minus 150 and plus 20. Now this is minus 120 and 70. And this one minus 30 and 110. Okay. Hopefully this works. And then the sticks here are formed from these particles, same as before. But I would like these to be... Yeah, these need to be... Actually, I don't need to push anything here. I can just define them like so. And this sticks in the same way. But I need these particles now here. And this motor is like that. Let's also log it here. And this one like so. And updating this, gravity or the force, whatever forces we will add there, we have just one for now. But basically, updating, constraining particles, moving the motor, the sticks, this has to go here in the leg. So the force is the gravity here, but this is now this. And the constraint here, this doesn't know about the canvas properties, so these are like bounds, basically. Let's just leave it like this and think about it later. So the particles get like that, then this motor updates, and then these sticks, one by one, they update. And the drawing here as well. So something like this. These particles, they all draw. When we update these things, I want to get this error logged. Or actually maybe returned. And this sticks, this sticks. And now leg update. The error is like that. We do that, and then leg draw CTX. Maybe we didn't break anything, and by we I mean me, and I'm sure I broke a lot of stuff. So I'm worried, but here goes nothing. If this is the only thing, yeah. Oh my. Okay, good. Yeah. Now it should work. Nothing shows. Was somehow my screen sharing broken or... Hmm. Okay, what disappeared? Was it my screen sharing? So now, with this simple code here, I want to be able to get from the leg the tip. Uh, and the tip is going to be particle 8. So now that this super complex mess is there, I hopefully don't have to deal with it anymore. Get tip location. Let's make it so that we get that directly. And now so the error. Now it's small, and now this path that is being drawn here seems to look not the same. Almost the same, but not the same. I think it's the gravity. Let's try removing gravity. No. This should be on the other side. It needs to stabilize a little slower, maybe. Yeah. Let's see how it looks like without the... Oh my goodness. Okay, now the error is small. Okay. This bounciness that happened there, yeah, it's because of this lack of rigidity in the segments, I think. I think that this you can adjust by doing here multiple updates in the sticks. Let's see if it makes anything different. But this thing here, yeah, I have to decrease again even more. So now, let's see. No. Interesting. What makes them bounce? Interesting. I have an idea. I did some mistake. Yeah, I will check if the error is small, small enough. But the problem I think I have is here in these sticks. If one of the points is not static, it moves. But if one of the points is static, the other point should actually move twice the scale. Maybe it's that. Let's be very clear about what we're doing here. If P1 is static and P2 is static, we don't do any changes here. Actually, we can do it like this. But now, if P1 is static, then P2 needs to change by twice this scale. Else, if P2 is static, P1 has to change by twice the scale. Else, both of them change by half. And now What is that? What if this thing starts to write something that you can read? That would be so weird. Uh, Something is breaking. Uh, let's do a draw here and return. So this was the original shape now. So what's the problem really? Okay, let me just decrease this even more. No, I think the initial setup is just too different. Let's do again this leg draw and return. And what was it supposed to look like now? So, okay, this is very big and that's probably causing some mistakes. Yeah, these new points here changed the structure so much that I think in the end I'm going to have to update these locations better. So let's just do that a little bit, make this angle almost straight. So 3 and 5, they need to be to the right some more. Yeah, 3 and 5 to the right, maybe 50 and 20. Okay. And 8 has to be also to the right. So maybe plus 20. Okay, and 6 and 7 a lot to the right. So also 6 and 7 minus 100 minus 80 maybe. Okay, this looks a little bit more like it. So let's see now what happens. Okay. What is happening here? Yeah, I really don't know what I broke, but I broke something. Yeah, good chaos theory. Uh, yeah, it's the idea, but for some reason it doesn't work. Because this point is now stuck on this side instead of going down. I mean, it's stabilized in a way that it's not what I wanted. If I could force this point to be on the other side now, it would do good. I'm more worried that this system. Okay, let's also reduce these many updates. I think that having a softer system, it might stabilize better, but no, it's still. So this tip should be on the other side of those things. And I really don't know. What did I mess up? Like this initial location, this kind of looks right. I guess I could put 8 a little bit more that way. But eventually I want to somehow change these values, play with different values. So, hmm, so if this system is not stable enough for that, then it's pissing off. I start to feel like, okay, let's see what happens now. Still going on this other side of the structure. Wait a second. So this worked just fine, and then something very horrible happened. So this worked fine, but then, yeah, it had that bounce. But then I tried to fix it. No, this is not correct. Oh, horrible. Now I get it. So this is not correct. The idea here is correct, but having this vector that is the size of this length added in both directions is a mistake. We need to calculate the difference between this and this length. I'm gonna call this diff current length. So something like this. Then I get the normalized, then I get the difference. Wait. Now difference is gonna be a magnitude. So it's gonna be, yeah, this length minus that. And this difference is our scalar. Okay. Let's still keep this name, this difference here, and difference here, because it's the calculated by subtracting the 2 points. The scale is going to be calculated like that, so it is a difference. But scalar, so this is a number, and then this new thing is norm. We don't need the average point anymore. We scale it by this scalar, and now we do the opposite. P2 is P2 add that. Yeah, this I should probably write it down, but This is subtract now. I should probably explain what I'm doing, but it starts to become that time when I can't concentrate well anymore. So let's see, did I fix it or did I break it entirely? If not, I might ask ChatGPT to do it. Ah, yes, I fixed it. um, I think this needs to be the other way around. And let's see now, does it still have that bumpiness to it? Yeah, still has that bumpiness to it. That, not bumpiness, but that elasticity somehow. So it didn't fix it. I changed the math here, I used a different approach, but this seems like it still didn't fix it. It wasn't the reason for why it's doing that. This error stabilizes, it becomes so low that it's not anymore the thing that is affecting. The lengths are what they should be, but something here. Yeah, I think we should be able to again try adding more updates here. No. I mean, if you think about this system in practice, it might behave like this if the joints are not solid and if this thing is starts to move with a very fast speed here. So it might actually make it behave like that. But I don't get it. What is happening? So it's here. It just picks up a lot of speed at this point and then it kind of slingshots it that way. Let's try something. Wait, particles are updating like that. Hmm. I think the motor can be before the particles as well, because the particles that are here static, these four ones, they are not affected by that movement, really. And maybe the constraint can come. It needs to come here. I'm wondering if, like, if we would loop this part several times, it might do that kind of movement off screen, so to speak. Okay. Well, this looks very similar. I don't have very good a very good brain power right now, but this is what I expect to see here. It's fine. I think, of course, I could say that let us wait until this error drops, but what I'm gonna do is actually update this leg in the beginning a few times, even before animating. Update a few times until the error drops. So big value. While the error is greater than a very small value, error is update. And now this update is important here as well. So the stabilization happens off screen, so to speak. Yeah. Yeah, I mean, sure. Yeah, when it's in the same direction. The gravity is actually still off, but I think that now the segments are so rigid that the gravity is not going to affect this shape. It does. It flattens it a little bit. You can actually compare gravity on and gravity off. Like if I set gravity to be, or yeah, if I do here gravity y is equal to 0, something happened there because I turned off gravity. But you can compare it with the next shape there. And you see it's a little bumpier because I think that the shape that is drawn here isn't really considering gravity in any way. Because these sticks are so thin that the gravity, it is considering, of course, if the gravity wouldn't be there, probably this shape would not be so in the same way. But here gravity affects so little this structure. Because these are indeed very rigid, and the way that the simulation is happening here allows for a little bit of flexibility in that. Of course, there's flexibility also in those sticks to some extent, but it's not really noticeable. So adding a lot of gravity here, like this, is going to give you a flatter form, but that's just because it's all these points are heavy like that. And okay, it's good to know. I liked the previous version here like this, and I think now we don't need the yeah, this is fine here, and we don't need the log anymore for this motor. And we also don't need this thing. Where is it? Index. Actually, this error tolerance, we wouldn't need to worry about that here. I think that the leg itself is doing this crazy stuff. So after we initialize this leg, maybe that's where we can do this thing. This update like so. Okay. Now these are globals here, but we could say this calibration process is here like that. So let's do that and then do that. And this one can have those parameters. So when the leg is created, leg calibrate with these and the last one, better leave it responsible for that thing. So now this object is easier to work with. And I think that I'm going to share this version on GitHub if somebody wants to have a look. So leg complete. Yeah. Oh no, I'm not gonna do this now. Sorry. As I said in the beginning, new computer. And I will do it later, updating the code on or I guess I could, if somebody wants it now while I take a short break. Okay. The beast is in reverse, is it? I mean, it seems to want to go that way, to the right. It touches here, assuming that this is going to be on the ground, and then, yeah. I mean, I guess you could put it in reverse. In the video, was it in reverse? Okay. Yeah, so okay, very good point. So let's not make this mistake. It looks like it is like that. So the motor could have a negative speed there. Doesn't really make sense, but But now it looks like in the video, right? Okay. Yeah. Yeah. Oh, really? Really? Good point. So some are in reverse. Let's see that 3D animation here. Yeah. So these are in reverse, actually. Interesting. Okay. So now the question is, what do I want to do with this leg? Because I have several things I could do. First is, could we find different versions, different values of those parameters that define a better shape? Now, this better shape really, I don't think we'll find it. Otherwise, Theo Jansen would have found it. But if we start with a different value, like if we have different numbers here to begin with, then what would happen? So let's say that we go with, I don't know, longer D and G. So our D is maybe 41 and G is, okay, 45 and G is 40 something. Then does this work? So it doesn't do a good job because this part of the at the bottom is not flat anymore. And this shape seems to appear here in these experiments, like maybe what we found now is something like this. So the question is, could we make the system come up to this shape using trial and error or using some kind of genetic algorithm like in this experiment? But basically, could we figure out these parameter values for these lengths there? And I think that I'm curious what would happen if, so L, A, and M, I think we can consider these ones fixed. Okay. L, A, and M, I think we can consider them fixed because they are like part of the structure that you build once, and then all the other things are the things that you might fine tune, but somehow the original structure maybe we don't need to change that one. So L, M, and A fixed, and A is fixed. Okay, maybe the motor is fixed. So A, we don't need to necessarily fix it, but somehow the motor here, I think that could be something that, yeah, motor and this supporting point or whatever. Yeah, anyway. But the other values seem to be between 38 and 65. So could they just be, let's say 35, 65, and then all of these, could they be random values between these intervals? So something like this. And now every time you refresh, you get some crazy thing. You get a crazy thing with different proportions. Every time you restart the simulation, you get different ones. And they create different patterns there with the tip of the leg. Okay, it was here. So in that experiment here, it seems to be that what he wanted to get is this kind of flat shape at the bottom. Yeah, so you could find out the real numbers somehow by maybe trying multiple of these. And of course, genetic algorithm is one approach. Let's see if we can implement that. But first of all, I would like to try to somehow automate the process. I can figure out how long it takes to do one revolution of this. And when this goes one revolution, I don't know how to prove it, but I'm pretty sure that this makes a complete loop. So then I do have the kind of amount of necessary information there. And if we have multiple of these legs at the same time, that's going to also speed up the process. So let's try to have a function here. Let's go at the bottom for now. Generate random leg. And x, y, I think that this is fine to give as a parameter. And then these things go here, like so. My music ended a long time ago, and I'm getting very tired. So now, very, very important question for everybody. How much do you want to see this thing walk? Because that will be the difference between taking iced tea or an energy drink. So, let's see, can I do a poll? So, yeah. Wait, not like that. Okay. Okay. Oh. Okay. So it needs to move in both directions depending on the wind. But if the bottom part is flat, then that means kind of that. So maybe that's why he was looking for this flat bottom there. Okay. Oh no. Oh, wow. Looks like the energy drink is winning. Ah, fine. Let's do the energy drink. Haven't had these ones in a while, so might have a weird side effect. Let's say. Okay. This path that the tip makes, I think that it's something I want the leg to compute. Banana, yeah. Yeah, um, this adjustment thing that happens in the beginning. So it's just a hack to somehow do what many people have been saying ever since the beginning with these polar coordinates and initialize everything based on those lengths. I should have done that. It's a very good point. Um, but this stupid approach to calibrate the thing in the beginning, like if I reduce this error tolerance even more, um, this beginning of the system, it should be fine. I mean, it would be the same thing as using polar coordinates with those given values, because the error is going to be like minuscule, minuscule, very small. Um, So I think that that's probably fine. But yeah, I'm. I don't think it needs to be that small. So okay, sometimes in the very beginning you see a little bit of an adjustment there. So maybe it does need to be smaller than that. Like this shaking seems to be gone now. Okay, still appearing a little bit. Still appearing a little bit. Okay, and then these shapes now, these crazy things are. Wow. So in the very beginning, until the system stabilizes, yeah. Yeah, and also one thing that we remember when we had that system not stabilizing well, like for example, if this point is here or on the other side of this segment, it doesn't matter. I mean, it's going to be a valid system no matter what. It could be here or there. It still respects exactly what the values of these things are. But of course, this thing here is not going to walk if this point is up there. So if you have a system like that where somehow this tip point is in the middle of the other ones, then yeah, that would be a very good observation that you maybe find a shape that looks the way you want it. Okay, but it but it wouldn't walk. I mean, this thing wouldn't walk, or if it would walk, it would do a kind of weird worm motion, something like a very big problem. Look at this thing. So yeah, if this shape would form somehow in the middle, it doesn't matter. So this tip point at the top there, other points would actually be doing the moving. Anyway, let's see. So I want this tip path to be part of the leg itself. One more thing. No, it's fine. Okay. I was thinking this update step actually uses the motor a bit. So the motor moves a little bit. And maybe I don't want that in the very beginning. So this update during the calibration step, it shouldn't move the motor. So it always starts at the top. I think that we have more control over that. It's possible that some systems need to move a little bit more before they stabilize. Okay, so now with this in mind, this tip path, it could make sense to have the tip dynamic so that it's the thing at the bottom. Like maybe there is a very weird configuration of this system where during the movement, first this is a tip, but maybe somehow at some point this becomes a tip because of some weird movement. So could it be possible that this is like the tip of a foot and then this becomes like a heel at some point and also continues to push. I don't know if it makes sense to you, but basically the tip doesn't necessarily need to always be the same point. I think what matters is that well, okay, here there is this extra padding in front so that it doesn't sink in the sand. But I guess you could put that on other points as well. So could there be some other configuration that pushes, that goes flat like that on the ground? Um, ah, let's just first try to reproduce what he did, not think about crazy stuff like that. But okay, so this tip position. So generate leg, calibrate. Okay. Yeah, lowest point. Um, you want to see the tension points. Okay. It's gonna be very small. I don't think there are very anything significant. But let's see. So when drawing the stick here, the color can be depending on this error. So yeah, let's do this. So it's going to be colored between yellow and So it's going to be between yellow and red, depending on the error. I choose yellow and red because green and red are... What did I do? Green and red are hard to distinguish by some people. So between yellow and red, the redder something gets, the more error is there. Now, we could calculate the error differently. To make it more significant somehow. Maybe like this. And then multiply this by something big. Oh, I think I got stuck in an infinite loop. This error now doesn't obey the same. Yeah. Let's keep it as a difference like this and just scale it up. It doesn't follow the same this threshold for calibrating is not anymore fitting to that one. But I think that we can multiply this error by something like 100, 1000, this. Now this calibration, we can also choose not to do it. And in that process, you see what happens. So it does work. It shows the lengths that are not the proper size. But after a very short time, everything is yellow. Even scaling this error very, very much, the difference from the intended values is so small that it doesn't figure at all. And if you do the calibration with such a small value there, you never see this thing happening. So you never see any kind of red thing. So basically, when the thing starts drawing and animating, we already have those values. They are such a small difference from the intended values that it's just due to like decimal approximation errors. I could have used HSL for that. Yeah. Red and yellow are also next to each other there, so I could have done that. Sorry, I read some of these things late. But, okay, where were we? So the sticks now... You know what? I'm gonna do that. The reason I'm doing this is actually because I want to start at orange. Um, sorry, I want to start at orange because I see it better. So now it's between orange and red. And just a quick check here, if the calibration is off, we should be able to see still those. Okay. We see crazy stuff. Because the error is so big in the beginning after we scale it so much that it just goes crazy in the hue spectrum. I Since it stabilizes so quickly, I'm just gonna leave it like this as a kind of Easter egg. So crazy blinking hues means errors. It's fine. Okay, now where were we? The leg is moving. I can draw it. Great, but I want many legs. So I want many legs. Let's say here at the bottom there are problems because the points are forced to be constrained. But it's fine. I don't let it go there. Okay, so now we have all of these shapes here. And you see some things start on the right, but not all of them. Like this one started a little bit on the left there. Okay, it's time to score them. So it's time to see which one is better according to some scoring function. In these kind of genetic algorithms, you would call it a fitness function. But basically, we want to figure out uh, if the bottom is flat or not. So somehow measuring the flatness of this. And I think flat just means, what does it mean? How would we calculate this flatness here? So movement where the y value doesn't change much, but the x value changes a lot. So big change in the x, small change in the y. And I think that someone said that the beast has to move both directions. So basically, we should measure this flatness only in one direction. Because reversing the thing is going to be the same but backwards. So maybe we can try to do that. Okay, yeah, Baruch actually pointed out there about some of the configurations not valid. Yeah. Okay. Anyway, let's get some kind of experiment going here and some way of scoring this. So let's have a function here, score path, and see what do we want this path to be. How do we want to score it? So going through the tip path like this, this is probably nonsense, but something like that. And let's say if current point x is greater than current point, then if previous point x is greater than the current point x, so it means that the movement is that way, kind of like what we saw in this one video. So I'm assuming this movement, so moving that way now. It shouldn't matter much, but anyway. So the previous point in the path, no, should be smaller x. So only then I only then I calculate. So tip moving towards the right. So tip is moving towards the right. I want to get the difference, like delta y value, and the delta x value. So actually, yeah, absolute values for these. And I could assign a score so that it's higher if delta x is big but delta y is small. So this could be one approach, I guess. Because if delta y is big, then we are dividing by it, so it becomes smaller. And then we have a score here. Now this score path, we could actually do that. And depending on the score, no, I want to do it somehow differently. I want to score the legs here. Okay. Okay, so first I'm going to move the legs. Then I'm going to score the legs. And then I'm going to draw the legs. The reason I do this is that I want to take all the scores out. Like so. And now I want to normalize the scores so that I can draw the legs with colors in a, yeah. Yeah. Maybe we use 0 at first for the minimum score, but basically with the maximum score I could normalize the values. So let's do normalized score like that. And starting at yellow, going to, no, starting at red, going to yellow, and then this normalized score, yeah, this should work. And now this path color is going to be like that. I pass it here. And when drawing this, I'm going to use that for the path color. So and now let's see how many bugs I have. This one is yellow because it is flat when moving to the right, but it's flat when moving to the right on the top part. I don't want that. This is also yellow for the same reason. So let's update our fitness function a little bit and say here, if this is like that, it's not easy because I need to know the whole path to somehow define what I'm trying to do. So notice these ones that are orange or yellow, they are really flat at the top, like what we are looking for, especially this one, but it's the other way around. Like maybe if I refresh and wait a little bit, I will find some that are good, but but it seems to be exactly the opposite of what I'm looking for. Like it finds this one apparently. Where's the yellow one? Here. Okay. I think this is also quite flat in that way. But this kind of looks more flat. I don't know. I'm not exactly sure why this is scored higher. Maybe it's actually very flat here and this one tilts a little bit. Yeah, this goes down a little bit. But anyway, we can scale these error values to get a better gradient if needed. Or even use more hues there. So now okay, it goes back to red. So maybe we start it at let's start it at green at 120 and let's go all the way to 0 or 360. Yeah. So now, wait, this is the opposite. I kind of like green as a good indicator. So now it's the opposite. And well, let's wait a little bit and see what happens. Mm-hmm. How much the standard deviation is of all the points in one rotation. Standard deviation in X or in Y? Yes, you could calculate it definitely. I mean, it seems like, according to this shape, it seems it's quite high. And I could imagine flat shape where the standard deviation is on Y is very low. I could imagine it as being good, but maybe this shape is good for a reason because when it lifts itself up like that, it allows for other legs to push on the ground. So maybe that bump is on purpose there. Otherwise, maybe many legs touch the ground at the same time, and that makes the thing not move properly. Yeah, exactly. Theolag is pointing that out. Sorry, I'm reading these in a little bit different order. Yeah, and probably many configurations are invalid. But okay, this one really looks like upside down. Otherwise, it's pretty good. Um, so actually, um, the sticks cross each other here in this one. I know here, for example, this can't exist in real life. But this configuration looks good, what we are finding now. Only thing is that it's kind of upside down. Okay, I actually think okay, the speed is not linear. Okay, so this actually moves very quickly here. Interesting. So this way it's fast. It's faster. Interesting. So if it's faster like that, yeah, standard deviation of the y values, because the differences are, yeah, let's try. Let's try. So then we don't even need the direction anymore, I think. But now it's crazy because we are looking now for some kind of characteristic that is not really visible here. I mean, it's very hard to keep track of all these shapes, how fast they are in one rotation. The shape itself doesn't tell us that. So you would have to watch the animation and figure out that that's also an important thing. And see that the movement like that has to be longer. But then again, let's just see what that is. So let's put I'm gonna put this one here, and the other one, standard deviation of the y values. Should mean that high standard deviation let's just see what happens and then figure out if it's proper or not. So for the y differences. Let's see. What is becoming green now? Yeah, I did it. Intersections and craziness. But what is red? Maybe I have it upside down. Where is the reddest one? Yeah. I'm sure there is some clever way to do it, but I think that I will do a similar version as I did the first time. But the thing is, so the score is like that with delta x, delta y in that case. Else, the score still increases, but with the other direction. Let's see what happens then. Because that should make it want to go up when going in the opposite direction. So delta y by delta x. Let's see what happens now. Okay, so actually, this green one looks again very good, but it's upside down. But now you can see it's tall. There are other flat ones as well, but they get a lower score because they're not as tall as this one. What happens if I flip this around? Not that. It doesn't matter because it uses absolute values there, I think. Hmm. Why are all good ones upside down? Why are all good ones upside down? And let's add the good one, like the very good one. Um, I want to add the good leg in the beginning because that good leg should be um, good. So whatever scoring function we get, it should get very good score, I think. And is it this one? What is that? How is this the good leg? It looks like the good leg. I think it's the good leg. Yeah, and it's always doing the same pattern. So how did it break? Why did it break? Did I do something stupid to it? It looks good otherwise, but something happens here. This one flips orientation for some weird reason. Uh, now it's very rigid, but for some reason. Wait a second. I think at some point I messed the values up. I think that's what I did. Let's look at the values again, because I think at some point I changed them to try something out, and then I forgot about them. So 38, 41.5, 39.3, 40.1, 55.8, 39.4, 36.7. 65.7, 49.0, 50. Okay, I didn't. I really don't know what happened to this thing. It was very stable before, and it looked so much like the one that we are trying to do. Like this, basically. Um, I really don't get it. What did I do to break it? Yeah, I find it a little not nice now. Hmm. Yeah, so looks like when gravity goes off, this pushes so much that crazy stuff happens there. Like the gravity is somehow holding it in place. That was just too long somehow. Well, let's see if the lengths of those, like maybe that error here. What if we scale it by a lot? Can we see some redness? I think we saw some redness there. Let's try even more. Okay, now it's so extreme, that error, that you actually start to see something, but these are those decimals that don't really matter. So maybe somewhere in between. No. Maybe now. Let's see closely here. Some redness appears there. So it's struggling to somehow fit everything in. Okay, let's try to do something. This rigidity, let's increase it a lot. And maybe where it's applying it, like here, this scalar. What if we make it a little bit softer? I don't know. Let's try. I have a feeling this does the opposite of what I want. Yeah, no. Let's just leave it like this. Yeah, let's just leave it like this and add that gravity that fixes the problem. Ah, okay. So this shape, okay, now this is the good one. I think the formula here is also not good for scoring them. Oh, I had a typo here. I forgot an equals. This might be also one reason why those other shapes were getting the better scores. Okay, here, this is actually getting a better score. Again, this bottom part is not where it should be. And what happens now if I replace this? Yeah, very weird. Well, okay, replacing that maybe means this is bad now because it considers the flatness on the way back. So actually, let's do it other way around. And maybe I try here difference instead of dividing and see what happens. Not good. Yeah, something is very weird. I just don't get it. very difficult to somehow find a way to score this curve. You missed a lot. A lot of back and forth. So I'm trying to score these curves and I'm doing a bad job. I'm also wondering if making the whole beast would be better and then scoring how much it manages to move in some direction. But why is this so difficult? Why? It shouldn't be difficult. It should be really straightforward. I want the bottom part of this curve to move mostly flat. But then again, okay, Peter pointed out that it should also move quite quickly up and down here. So it looks like it's moving much quicker this way. So quicker that way, but actually the visualization I have here, it doesn't see, it moves a little bit faster, but not that much. Okay. And now this is green, so whatever function I have here is doing something. I think that we need to consider the full curve. So this motor moving, updating here, I would like to know how much it moved. This angle, basically. So I think this angle can be 0 here. We use radians. And we don't need to calculate it like that anymore. We can just increase it like so. Now let's see if this changes anything. It changes the initial start angle. It's now pointing at the right. But this means that when this angle reaches now why is this path drawn there in the very beginning? Oh. I shouldn't. Why are we recording that path? That path shouldn't be there. This error tolerance here. So that path shouldn't be there for the calibration part. Here. Okay, so now it's still there. Why is it there? Oh, it was handled before already because I put this tip path to be 0 after the calibration phase, or a new array after that happens. But why is it still something there in the beginning? What makes that line there? Oh, it's the motor moving. Yeah. Yeah. It's the motor jumping from something to the 0th angle. So let's have minus half pi there, and then we don't have the problem. But then when the motor angle is going to be pi, so exactly here, then we can do the scoring. So then we have the complete path, basically. So let's have score is 0, and score path greater than, now this one starts at minus half pi. So if it's greater than half pi, greater or equal to half pi, and let's put no score there, so let's put it null in the beginning. Then we just do this, and the score is gonna set that value. So this score is 0. And now I'm not changing the formula just yet, and I don't need to return this anymore. I just take the score from there, and everything should be null in the beginning. So this gives everything orange, but as soon as it ends, it's not happening. What is even happening here? What's this crazy stuff? So it's not happening. Oh, angles are going negative. I forgot it's moving that way. Yeah. So actually, less than 2 pi minus 2 pi minus half pi. Yeah, I think this should work. So let's try again. Everything should be orange. And then the moment it ends, the scoring happens once. Okay. So now whenever we score the entire path. And we could calculate a kind of a measure that takes into account the bottom part of the path when it's complete like this. Okay, now this one is high for some weird reason, so the formula that we have at the moment doesn't work. Like this function just doesn't work. But now we know that at this stage the whole path is available. And could we now use something else to measure this? Like, for example, we want the points that are below in the bottom part of the path to be many of them. So a very different approach. Let's go and take the average point location, or no, the bounding box of the path. So Okay. And now with these, we calculate a position that is maybe like a third of the way, or I don't know, from the bottom part. So let's put 0.7 here. And if there are more points below this, it means that the bottom part is moving slower. It shouldn't be. Like a circle and moving at the same speed is going to be um, equal. So if you take the center point, but then if you move it down like 70% in this case, you have very few points there because most of them define the top part of the circle. So really what I want to do now is just count the points that are underneath. So something like this, and I just put the score to be this length. Let's see what happens with this one. So very different approach. I don't know what's going to happen, but this takes into consideration the number of points, and I think, oh boy, why is this one so green? Okay, it had some calibration in the beginning, I think. It had something in the beginning that the others don't have, like this one. So it affected somehow the... I think the formula is fine, but why is this... Okay, this one here got also good score. I don't know if it's better than this, but it got some score. Yeah. This one again, it has that weird thing in the beginning. I think it has to do with this calibration. Oh, great. And now I made the error so low that I'm stuck in infinite loop. I think this is okay. I don't know what to do about that calibration step. I guess that I could actually not use the error here, because if I set the value too low, yeah, I don't think we need the error tolerance. We just work until the error disappears, basically. So yeah, let's put something like this, and then while error is less than the previous error, we update it. Previous error is now the error, and we update it like that. So this calibration should work for each of the shapes really until the end, until the numbers are the same, basically. Okay. So now this one with the really good values is still at the top here in the, it's still green. Yeah, seems to be green. There are others that are green as well, like this one. But I don't know if as green. We could also make this the value for this bottom, it could be even lower, like maybe 0.8. So now the bottom part of the curve really focuses on this part from there. Okay, what even happened here? Oh, some crazy invalid formula. But why does it score so high? It's because this part at the top goes away very quickly. Maybe. Hard to tell. Okay. Anyway, this one looks good. I guess this has the bottom 20% quite low, and it's moving relatively a lot here. Like all these points, probably now it ended. So yeah, it's comparable to this, but it's so crazy that we don't care about it. Okay. Yeah, Adrian points out that some need to be in a straight line on the ground and then above. Yes. Okay. So now we try to make it walk. Or let's see what happens with these values. The first one is the one that we have to end up to, so it doesn't count, Daniel. So I was just debugging to see if the function is giving high scores for it. And it seems to give. So this kind of fitness function seems to be okay. But look, now this one became better. And Why is this thing here still up there? Okay. Let's keep the function, the scoring function as such. And I'm going to take out here this leg that is generated with the known best values. And now everything is really randomly generated. And we should be able to get some decent variant from here. So we got this one and this one, I guess, two of them. So could we try mutating this in some way? We need these parameters to be stored somewhere. Okay. And let's add a static function here. Mutate a given leg. And now everything except L and M. So, okay, this mutation rate. This min and max is something, okay. I think we can just move in some kind of direction. Yeah. Mm. Let's do something like that. Something like that. And this goes for everything. I really regret not putting these parameters in some array and dealing with them like that. But because they had names there, this I'm just going to keep as such. So okay. So this max score is 0 here. And then when it completes the round, it becomes something. So then everything is like that. Okay. And we can have some kind of button here, maybe below. So now I want to take these legs, find the best leg. Um, best leg or best legs. Let's just go with the best leg for now. So something like this. And now I want to mutate this best leg. So this, okay. These are fixed values. Legs, we take it out as a function generate legs. And this one has the spacing here, and it does that and returns legs. And here we generate the legs with that spacing. And here we can have, why is this so ugly? Yeah, we generate the random legs, but reference leg is null. So here, if not reference leg, then we generate random legs. Otherwise, um, push reference leg mutate. No, it's not that method. It's leg mutate. What was it called? Mutate. Leg mutate reference leg. Oh, X and Y should be there because we don't want it to be in the same place. So this doesn't come from the origin. It comes like this as parameters. And like that. So this generate legs is called there. But here when we call it, we give this best leg as parameter. And the spacing is this global variable. Okay, so now this should work. But if this max score, if max score is 0, then next round this button shouldn't be pressable. So let's put here also an ID. And let's see how many things I broke. So, okay, and I want a line break here. Doesn't work. Okay, so if the max score is 0, like that, otherwise like that. And when we mutate, let's try to force now the mutation here. Let's put it to 0 because I want to see if after the mutation all the legs turn to the same leg that was good in the previous round. So okay, so for some reason this is a good leg now. Yeah, some weird thing happens in the beginning. Let's see now if the next round all of them turn into this one. Error. Reference leg is not defined. So Oh, typo. Yeah, typo reference, thanks. um, I don't know what I'm doing anymore. Yeah, okay, so I can. Yeah, okay. Baruch is pissed off because I'm not using an array. I'll try to do it. It's just uh, I'm getting tired. Okay, so now this one hopefully comes back after this next round. So what happened? Nothing happened. Of course, nothing happened. Ah, okay. So now the best one is apparently here, maybe? Okay, let's see if this one gets replicated. So, yeah, seems like this one starts to have a lot of copies of itself. But that also means that there shouldn't be a winner anymore, or at least I can't really tell any difference. So it's exactly the same. But if this leg is going to be, if we are going to have some kind of mutation rate there, now this, without trying selecting multiple of them and just doing this, it leads to some kind of local optimum. So now this one is going to mutate a little bit. You can see they're a little bit different, but this seems to be a bad start anyway. So this way, without having multiple versions and then maybe crossover, it's not going to be so good. We would have to start all over, because if not, then these are too similar to each other, and then the mutation rate could be actually used as a parameter, so that you could play with that after each iteration to some extent. So generate legs here. Um, mutation rate, XY, mutation rate, and this step size, I'm just going to keep it fixed there. So seems like a reasonable value. But now this mutation rate, I need the kind of slider there. So yeah, something like that. And I just use here mutation rate value directly. So okay. So let's see what happens with this one. Basically, if I don't find anything that I like or anything promising as the best candidate, I guess this is now like a best candidate here, maybe. So let's just go on with that. And it looks very similar. All of them look very similar. So in the next round, I'm going to try to increase this and see what happens. Yeah, crossings are bad and they could be removed as a kind of clear separator. They are very similar to each other. I wonder if this mutation works. Okay, now they are a little bit different. But 100% doesn't really give me... They look still very similar to each other. So that initial size, so this one here, this really depends on the size of the canvas and the size of these initial values and the unit that you use, and it's like a scalar there. So maybe we try more like this. And we shouldn't lose the best one from previously, just in case it's something really good. Maybe now this is the best. It looks very weird. But let's see. Yeah, that one was the best one previously. It looks really strange. Yeah, let's try more like that. Now this thing got kind of in the way. And it's because of this weird thing that happens in the beginning. I don't know why this calibration, for some reason, it still fidgets something after that. And it's problematic because that kind of quick snap is making the shape have many points on the bottom very often. So I think that one way to avoid it is to do one loop without recording it. So a different type of calibration that might work. So basically, this update here, okay, it would do that. And then after this, so very messy stuff here. I regret many things, but it should be easy to fix once I would not be so tired anymore. I think maybe starting over with those coordinates, and I'm not sure. Anyway, here calibrating, so doing that, and then while motor angle is that, update with moving the engine and without scoring the path. So not scoring anything, doing that. And now we reset this motor angle like that. And I think that this should do something different, like avoid those weird paths appearing in the beginning. So maybe we got rid of that now, because it didn't seem to happen on a second attempt, like in the second loop. So now we get this path as a good path. Okay. And when we mutate that reference leg, so I want to keep it. But not as such, because if I do that, it's already processed and it can create problems. So I mutate it with the 0 mutation rate. Okay, very messy now. But let's see what happens now. So the previous one should still be kept. The previous good one should still be kept, even if... so this should be somewhere. Kind of looks like a very symmetric thing. Should be still somewhere after this, even with the high mutation. So very symmetrical, like an arrow pointing there. Error, great. Legs. Where is it? Oh. Snapping any point. Yeah, I think that would destroy the beast. Maybe this is the best one, or why is this good? Ah, okay, it spends quite a lot of time at the bottom, but it doesn't move very much. Yeah, our definition for the scoring function is not very good, it seems. And what is this crazy thing here? Oh no. We are still not... Oh my. Even with this weird calibration, it doesn't work. It doesn't do anything. Oh. Yeah, I was wondering why it doesn't stop like that in the beginning, because it basically has to pre-process the whole loop for everything. And that takes effort. Okay, so now this thing is good, apparently. It's horrible. Let's mutate it a lot and see if we find this horrible one still somewhere. Yeah. Uh, I'm not sure if it's this one or. Oh, this one. Yeah. So any of these snapping movements, oh my, so many of them are snapping now. And they are repeatedly snapping, so it's not anymore some weird initialization. Oh, this is crazy. Yeah, so actually, the function that is scoring the things, if the tip of the leg is stopping there at the bottom, almost stopping, but moving really slowly here, those are counted as a good thing. And it's not a good thing, I think. We need to score it so that we don't just count, but the tip is moving a significant distance in this bottom part. So maybe that's what should be here. So the score should be the points below y. We calculate the distance that they traveled, the delta x basically. So okay. So let's give it another shot. Okay. Okay. More decent. It looks a little bit more like the one that we are trying to reproduce. So basically, in the bottom part of this curve, it's trying to cover the most amount of distance somehow. No. Oh. Yeah, I don't need to animate them. But it's kind of like mysterious to see what is coming up. But you're right, I could just instantly see what the results are going to be like. Now I kind of like this one. Let's try leaving a low mutation. So it's kind of like what you say, decorative purposes. But yeah, I'm getting tired, so I think that I don't mind watching these for a while I still think, okay, it's getting something to some state that looks in a way that it does move. Um, but this is like exactly the opposite of what I want to have. Because it's moving slower at the top and faster at the bottom. So what Peter said before also makes sense, that it should stay longer time on the ground. And now we're not considering that. We are just considering that the bottom part has a lot of movement. So it is significant, but actually the top part has even more movement now. So maybe that's actually the thing. So points below y should have more movement. Mm. I really think that there is a clever mathematical thing that we could use here instead of doing such an artificial thing with this threshold. We don't even need a threshold if you think about the distance covered below should be more than the distance covered above. Yeah, if the threshold is half. So um, we could say x below. Yeah, sure. But here I want to do a subtraction. So I want the number below to be bigger. I want the score to be bigger. I could do this. Let's see what happens. So ratio now, let's call it that. And let's do that. And I think this might work. I don't know. So the idea now is it's not going to work. Definitely it's not going to work because it's going to be the same. Oh, I hate it. Yeah, let's see what you guys are writing. Yeah. Mhm. Yeah, number display better than colors could be something. If it has the most points on same x-axis. Horizontal movement, yeah, while on the ground. Yeah, I mean, all the legs will be the same. That's not the problem. But Peter was pointing out that the top part should kind of happen quickly and then the bottom part should happen slowly. Yeah, on the ground, many points and in a straight line. I agree with that one. Many points and in the straight line. But it also should cover a lot. So many points in a straight line can also mean a very small line. That's the problem. Maybe it moves like that, and then at the bottom it just makes a lot of points very close to each other. How even the distance between the points on the ground. Yeah, very many ideas, but uh, when you define it like this, so that it should be a straight line, but then the length of the line is also important, then it becomes this kind of multiple objective optimization, and that's something else. And if we calculate the mass here, like the center of mass of the points, like it moves a long distance here, but also slow, so there are many points here. Now our center point is here. So basically we are comparing this like minimum maximum x from this center point. So at the moment what okay, this doesn't have that, but so if we draw a line here, then maximum x, minimum x for the top part, and maximum x, minimum x for the bottom part, it's much larger. So so this should work. Let's try. Oh, okay, we got this one. Okay, now we're getting these crazy ones. So you see the definition is not good. So yeah, here if you divide like that, the difference here is really small. But then the bottom is, yeah, this is better, looks better than the one that we are looking at here, if we think that that's the good thing. But actually this point becomes below the base. So that's also another problem. So now mutating these probably is a waste of time. Let's try more randomness there. Yeah, the knee gets lower, exactly. It's not good, but the shape of that one point that we consider the tip was better. And what even happens here now? This is so pissing off. Okay, and then what? Okay, some snapping. Yeah, this snapping now, it's snapping there a little bit. So if I define it that the shape should have a pointy tip like that, this was a okay result if you allowed that snapping. So damn, really hard to come up with a good function that describes that. It should be really easy, but it's not. Manually selecting them, that could be something that we could do. So manually choosing the one that has a chance of being it's going both directions on the bottom. Yeah. Yeah. Okay. Okay. If the sticks are crossing, then it should discard that. Fine. I take the challenge, but I need some iced tea. Oh boy. So during scoring, if we score the path, if we scored the path, so this calibration doesn't score the path. But when we start to score the path and we see the animation there, so the reason I don't want to remove the animation is because I would have to do 2 loops. I could do it. It's possible. Let's see if we can do that. So we calibrate like that, and then we do this one time, and then we do it again, scoring the path. So the difference now is that we wait a little longer in the beginning. Oh, this has to go here. So the path is now already there, and I can see this good one. So it takes a little bit longer in the beginning because it does 2 loops now. The first one for this calibration, weird stuff that is an annoying thing. but then it jumps to do this one, and yeah, okay. And now for discarding it. So during this step, if any of the segments are crossing, then it's a problem. Okay. So oh, and actually this scoring should be after the movement and after the particles and everything is like that. And even after this one, so here. But if we are in the process of scoring the path, even before the angle reaches the end of the period, we can check if sticks intersect, we discard. Yeah, like that. Sticks intersect. Was it like this? No, it was like that. But this doesn't exist or what? Yeah. Okay. Okay. And now this one needs a method for checking the intersection. So I might be okay. Okay. So let's just debug visually, and if it doesn't work, we figure it out later. But basically, any discarded thing, okay. If we found an intersection, I think we can put the some marker for that stick. And here the color, something like this. Let's see. Okay. So all of them are discarded. because I don't know why. Well, probably the base and the motor. I mean, these sticks are probably okay, but have to limit to only some of them. But the thing doesn't work. I see many other intersections and they are not lighting up. So it's not working. Um, okay. The imaginary 0, 1, and 4 should be ignored, probably. But first, I don't understand why not more of them are marked as intersected. Oh, it stops, it breaks. Sure. I want to see all of them. I don't care about efficiency here. I sure saw all of them. Okay. Are there any of them that don't intersect? Yeah, it shouldn't be an intersection to all of them. Yeah, maybe it's flawed. I have to check again. Let's try another AI. uh, let's see. It could be something here at the borders, or this determinant. I don't have patience now to look. Let's see if somebody else has a quick look. Okay, this is what I'm thinking. Mm-hmm. Yeah, I think that's what I want to check. Let's see if this improved version works. Using AI after another AI. Um, no, thanks a lot. Yeah, something is definitely weird. Actually, I don't understand why this is minus here. Now it's better. Thanks a lot, AI. Yeah, this is better. But like somebody mentioned before, 014 I have to ignore. What even were they? So 014, yeah, L and A here. I have to ignore them. So yeah, where was Baruch's code for putting these in some? Okay, but yeah, the spreading there this rest. Um, I guess it works, but I still need to look at these now one by one and ignore them in the intersection. And thanks for the help, but I just suffer. Uh, yeah, this would need a little bit extra thought, really, uh, planning how to structure the whole thing. But okay, so what was I doing? L and A should be ignored. So A and L. But actually, I'm not keeping them as variables, so the solution can work. Let's try Baruch's approach. So it was in the leg, I think. This constructor. He said to do this. Yeah. But how do I do this assigning the values? How do I assign them there? I seem to be using them somehow. Yeah, let's not worry about that at the moment. Sticks intersect. So here I have to skip some of them. So the first one should be skipped 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This code is going to be fantastic. And now we work with these selected sticks only. And now if I run this again, okay, so here looks like there is some intersection, no intersection, even though these things here intersect. These two links are not considered, so it's fine. Okay. Seems to be something. So if the sticks intersect, like here, this path, this crazy green path here shouldn't be considered. So if the sticks intersect, something like that. So let's try again. Okay, we are getting something like this now. And like this. Let's see which one is going to be selected for the next round. Okay, I think it was this one. No, it was the other one. So some of them get discarded here. Okay, let's mutate a little more. Also 1, 2, 0, 2. All right, 0, 2. So M here. So the one after. Why in the next round the calibration thing doesn't happen? Yeah, that's a problem. So in the beginning, we generate the legs. With this one. Generate leg also calibrates. So when we mutate, um, okay. So one of these is the good one. I guess we could select multiple of them, like really make it as a genetic approach. But let's see now. So I have a feeling I did something horrible. So oh, I'm not adding it here. Yep. They were doing the calibration and everything, but off screen, sort of. Okay, so now I'm getting all the processing done behind the scenes. So why is this path now good? It goes down, and then in this bottom part, okay, it goes one way, but it also goes backwards. So actually, so in the bottom part, it does go a long distance, much more than in this top part, but then it also goes back still in the bottom part. I don't want that. I don't want it to go back and forth in the bottom part. What was our scoring function again? So in the bottom part, bottom half, min x and max x. It's a problem. It's not what I want, because it can come back all the way in the beginning and then go up a little bit. And it still scores high in this one. So the bottom must be a traveled distance, but only on x, really. So going back should penalize, really. And hmm. Let's cut out these maximum points and try to do it in a more clever way. Yeah. Okay. Bye. I don't want the absolute value here. I actually want the difference with the sign. Why are all of them orange? Oh, it was because they all were bad according to that function. Okay. Now it's kind of okay, but another disqualifying factor is if another point becomes lower than the tip point. So let's do that as well. Uh, okay, this gray one, it goes below, and this gray one goes below. So they are red because they are discarded. This is okay. It's kind of the opposite, but none of these ones look really good. I think this is the best, and it's green. So okay, snapping here. This is the best. Why? I don't know why this is exactly the best. Actually, I kind of know because we are in the middle point. I think it's time to get back to using a bottom point, a more bottom point in this one. So maybe 7, something like this. Because, okay, now all of them are probably bad. I guess that can happen. Yeah, this is tough to get a good one, I think. Let's try 6. Okay. So randomly generating them seems to be very unlikely to get a good one. They are all disqualified by some reason, like gray points here or intersections there. Some of them are okay, but I think that the scoring function gives a negative. So I think that the scores are negative. That's why we don't see anything there. Which, I mean, even negative scores could be a start if we lift them up a bit. But I think that the function doesn't work. It's just those kind of weird shapes also seem to count as good shapes. Let's try again that basic one with the point count. Yeah. So the tip here, it's not traveling much distance, but then the problem here is going all the way to the right and all the way back to the back. So it's horrible. How about using the area somehow? Like if you look in the bottom part, the area here, the elongation. So this looks very thin, but here this top part is not as elongated. No, because it could go like this and then back like this and then have a peak, and it's the same issue. Why is this so complicated? And how did he do it? Because I couldn't get it from the video. That detail was omitted, I think. Difficult. Yeah, very hard. Let's try another approach. Instead of this point at the fixed value there, let's try the center of mass. Not like that, but with the points themselves. So something like that and like that. So now I'm getting the center of mass there. And maybe I'm going to also put it as an attribute so we can visualize what I'm trying to calculate here. And then from the center of mass, if below the center of mass, the y variance is low compared to above, or use two values. How far the center of mass is towards the bottom. let's just say let's try this second scoring draft again, because so many things have changed that I want to see that one before doing the center of mass. No. But yeah, back to the drawing board. So maybe if we calculate this standard deviation of the x's above and below the center of mass. Minus the one above. Let's see now. This is opposite. Is it opposite because I messed up something here, so the standard deviation below? I don't want the y value. Or if I use the y value, I wanted the x value. But if I use the y value, it could be that yeah, it doesn't seem good. So it goes like this because then on the top part, the y difference is big. But again, I actually wanted to use x here and the formula like before. So I'm kind of getting this shape now. Where is this center of mass? So after this line, let's draw also the center of mass. Yeah, like that. Let's put it same as the path color, maybe. So it seems to be quite high up. I don't want that. I would like it to be at the bottom because that means a lot of points at the bottom are pulling it towards the bottom. So maybe we don't use any of these. So let's start with just the difference of the center of mass from the center bounds. So um, hmm. Okay, and I guess I want it to be normalized. I also want it to spread horizontally, which we don't have at the moment. But let's just see what happens because maybe it happens by default. Yeah, now it's at the bottom, but that thing is not good. It's very close to the bottom, but it doesn't matter. All of these seem to... What is this? Okay. This path seems to transform itself into some kind of very thin path. Let's try to calculate also the area of this path. So, you can use this formula. It should be correct. So y offset is this, and we want that to be big, and area, let's call this compute area, and then here okay. So now if I put here the area, I should be able to see circles coming just with the area alone. So this should somehow gravitate towards big circles or very round shapes like that. Of course, if somehow this structure makes for an elongated shape, that's also fine. But I want the center of mass to be at the bottom. So somehow many points here at the bottom part. And I think I have to somehow multiply these two. Now let's see this offset. So the difference to the mean y, and now this is going to scale the area. So if it's going to be very close to the top, it's not very good. So let's repeat a few times and see in which direction this is going. Okay. So if I just leave the area there, if I just leave the y offset, it's gonna give me points that are at the bottom. But if I multiply it with the area, then why is this not combining the two? It could be that this area is more dominant in this case, so this other one doesn't matter much. But I think that in this initial case, you should get something where this is also closer towards the bottom. But this area is so big that it's basically now halved because of this other percent value, and then it's still better than all the other ones or something like this. So maybe this y offset should be more dominant, but these are values between, yeah, maybe we don't normalize it. Let's see this thing. And Okay, weird stuff happening there. Very tricky problem. I don't know why. Maybe should have somehow. Somehow this center of mass seems to want to be at the top instead of at the bottom, and I don't know why. I'm taking this, the minimum y value, and then the center of mass, the lower it becomes, minus that, it's going to be bigger. So the lower the better. But yeah, I actually want to normalize it so it's between 0 and 1. But then here, maybe I have to use something like this. Let's see. Okay, it's getting somewhere. What about a lower power here? So maybe okay, weird stuff happening here. Okay, maybe this area, because it gets too elongated like that, if I don't have it in check somehow. Maybe I could measure around this value for this area. No. So okay, and now if I do this, Okay, so now this roundness here should give me circles again, but now it should really make them circles regardless of the size. But they should become more and more round with each iteration. So this seems like it works. It doesn't increase in area anymore. But what I still want to have is that, and now this number is between 0 and 1. So like that, and the y offset is between 0 and 1. Bigger is better. So now the final score, I can try this. And one problem now is that that distance that it's covering, it's not taken into consideration so much. But it should find relatively circular paths that are having the center of mass closer to the bottom. So that means that the points at the bottom are moving slower. It doesn't seem to be the case. Oh, damn. These ones here are touching the side. Oh. Oh, so many things. Oh, no. Did I square that value? I wanted to square root it or raise to a fractional power. Hmm. Getting something a little better. let's try to optimize in smaller steps now and see what we're getting. So seems like I'm getting this kind of triangle shape. Now I don't really want the area to be bigger. What if I raise this to a very low power like that? Does it make the triangle more pointy? Because I think it will. Let's try adding them up and then with multiplication. So now they're equally kind of important, but this area is a little bit hard to understand because it has a square there. So okay. And now with this addition, let's try multiplying this one or raising it to some fractional power like this. I really want this to go down, like significantly down. And it could be just very unlikely to reach those configurations, but why is it so easy to get the point to go up but not down? How about I try the opposite? So this one. Huh. Let's multiply by 2. Multiply by 5. Now this area thing starts to lose importance. I really don't get it. I think that now I should be generating those kind of triangles, and that's okay. But really, this center of mass should be lower. I think that this kind of transformation that I'm doing on the sticks is just unlikely to generate those that have the center of mass at the bottom. So this is clearly selecting them at the top. Right? I mean, it looks more up than the middle. And as a result, this means it's moving faster here and then slower at the top. But I want the opposite. I want it to move slower at the bottom. What if I do? Probably everybody noticed by now that in the last hour or so, there's no, like, it's mostly trial and error. I do have some ideas what I want to do, but can't go deep anymore and think about the issue. I just can't figure out why combining the idea that I want to go low. So the Y offset should work. If I just put the Y offset there, I eventually get these. Or do I? Why do I get? I don't get them. It's opposite. This is just going to give negative scores. I don't know. Why am I doing this? So for some reason that I just can't figure out, I think I need to do 1 minus here. But maybe I'm wrong, let's say. So this does move the point below in the bottom part, but it also forces this to be a line, kind of a curve like that. The area is not taken into consideration. So that's why I want to multiply this or combine it in some way with the area so that the area becomes something else. Something bigger. Now something weird seems to happen here. It's causing this kind of weird tear shapes to appear. And that's why I think I need to do something to this one. And actually, I really think adding those is necessary. Mhm. Getting those triangles again. But that point seems to be in the middle there. So again, I lost this kind of Y offset component. Let's keep it alone, leave it alone there, and see what happens when we square it. Does this point get even closer to the bottom or more towards the top? I think it might go more towards the top. So maybe the square root here. Yeah, I really don't know. Some combination of this should give me what I want, but yeah, I don't know how long I'm streaming. I'm still uh, stuck on this thing. And it's one of these moments that I probably should have given up a while ago. Let's try repeating this a lot. Darene, am dormit. Am adormit. Nu mi iese ceva. Oh, actually now they seem to get closer to this bottom side. Half of the path points are as close to max y and the total height of the path more than 20 pixels. Yeah. I mean, yeah, you are right. But then this 20 pixels is something very specific to this particular simulation, and half the path points are close to max Y. Total height should be 20 pixels. So basically, a thin line like this that is 20 pixels, but it just goes down and then lingers there for a while and then goes back up. It is 20 pixels in height, and it is with most of the points close to max Y. So it sounds like a descriptive thing, but when you try to put it in practice, surprises like all of these things that I've been getting now start to come. I think we are getting something here, but it seems to take very many tries. But this point does seem to get a bit lower. Yeah, probably some other rule is needed. Let's try lowering that. But really, when we do this, the problem is the shape becomes smaller because the area of the shape is no longer important. So I don't really want that. I don't want it that low. And I want the shape to be somehow long also, like to do that step. So at the moment, I kind of got it to work. Be as wide as possible, more width, yeah. Be as wide as possible. But we are getting now those very long things that are very wide and also back the same way. So the thing steps and moves and then moves also back, and we did nothing basically. So really, area is one thing, but because I want it to lift up. So that's why I want the area. I want it to lift up. And this center of mass here of the points should make what Peter said in the very beginning, that it should move slower on the bottom side than at the top. But it doesn't. Because this triangle is anyway pointy towards the top, so there are fewer points there and more at the bottom. So the center of mass actually does get lower. But it doesn't make the movement at the top any quicker. Now, I'm quite sure that these shapes will walk. This shape will walk, I think. But we don't get those magic numbers that that were in that system. So maybe I'm gonna say stop to this and choose one of the best outcomes here that I'm calculating myself, and then also use the magic numbers and try to build a walking system with these. and then I'm done. Yeah, let's do this kind of final stretch here. So I'm just happy with this result from here. Let's take these values. So I'm gonna put here at the top these are from the video, so like that. And these other ones are from me with this optimization approach. So oh, okay, actually all the way here. So A is here, B, C, and so on. D is here. Okay, so now this is my A and my B and my C, D, E, F, G, H, I, J, and K, it's not really a genetic algorithm with only the mutation there, but I think that if the function would work, would be a good one describing that kind of shape, you don't really need it. I think mutation could narrow in on a good result. It seems to narrow in on what we are describing there, but the thing we are describing is not well described, so to speak. And the last two values, we didn't change them. So those are like that. And now, so this is now generating them with the mutations. So this is generate legs for optimization. But generate beast and this one needs to be a little bit different. So the legs are an empty array, and let's generate one in the middle of the screen. So like that, and generate leg with those values. So Okay. And after that, what happens? I guess nothing. So legs is not iterable. We have to return the legs containing just one leg. And now it's in the center screen, and it is moving according to that path that we did. Okay. So I want this shape to not be I want it to not be stuck on the wall here. And I think I want another segment here to keep the thing rigid. So, I don't want to also break the rest of the code. So I'm gonna do bad stuff here and tell this leg to so what were their names? It was 0, 1, and 4 is static false. 0, 1, and 4. And where is it? It's not there. Oh. Okay. 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 It's very interesting. What isn't happening? What is happening? We are missing that one segment, I guess. So this one segment between this one stick between the particle 0 and 4. So let's do that also. Like sticks. Push new stick from particles of 0 and particle of 4. And I guess desired length should be just the distance between them. It's calculated automatically. And now if we refresh, yeah. Wait a second, why is this shape intersecting? Oh, it's intersecting that one segment that we added now. Which shouldn't be considered. But it's okay. I mean, we don't use this shape for... Yeah, we don't use this shape for optimization anymore. Let's keep the first one static. Okay. Something is very wrong. Yeah, there seems to be a lot of tension in these lengths. Hmm. Yeah, it's I really don't know. So this tension is appearing there like crazy. If we put the values from the video, let's see, does the tension exist for those ones? I think so. So something is wrong now with this calibration, or it really went crazy all of a sudden. Like, yeah. Yeah, okay. Yeah, TypeScript. I did consider it. Maybe I will change to that someday. Let's see. And JS doc as well. No, I think that somehow this updating the sticks, it shouldn't do the whole thing, but like now I'm moving the maximum distance in both directions, but maybe it could do it a little bit softer, and then the repeats are going to settle in a less um, in a system with less tension. Now basically nothing is static there, so everything is here. So no. Yeah, I'm overly tired now. It doesn't seem to listen to me. Same. So this is the soft variant, and this one kind of works. Let's also link this one. So now this segment here should be holding everything up nicely, but it doesn't because of this rigidity here. So now it's a little better, but this gravity seems to be... Maybe the gravity is very high. We just didn't really... Yeah. Well, it looks fun. And it's kind of like some crazy AI creature that all of a sudden decides to kill us all. Yeah, floating point approximation. I think so. I think that's what happens here when scaling these sticks to make them the same size. Um, why is this gravity so strong? I know! Here, this I think shouldn't be there. The gravity was being multiplied by that. But I think it should still update a little bit. Let's try again. Yeah, I'm not making any sense now, and I know that's the case. But I want to get something working. And, um, okay, it's falling. Is it falling? It's pushing against gravity. Now gravity is so small, it's drawing something. It's so funny. Imagine it's like something like when you have a dandelion and you blow in it and it's just like floating in the air. If there would be some kind of small insect on it flapping its wings, it can also go up. So the gravity now is so small because I thought it's too strong. It was too strong because I was repeating that thing there many times. But I want it to fall like this. So this is fine. Um, yeah. So updating this one here, I think the constraint should be after this. So let's do another loop here, because we want that to be after these segments, these sticks are fixed. But then the update here, I think this is fine. Let's see, refresh and making them fall. Not fine. Okay. Okay, it should be before the sticks are modified, maybe. Then the sticks are already constrained by, the particles are already constrained here, so the sticks can't get out of bounds. So, okay, that's, maybe that was a bad idea. So now when this falls, is it more stable? Not really. Not really. I think this rigidity might be also very high now. Maybe this is stable enough. Or maybe not. Nope. It's Pikachu. I guess you mean the drawing that was appearing previously on the background. Yeah. Okay. Something is really collapsing it a lot. Especially when it falls on the ground. So somehow those forces, this thing pushing it back up, it's causing problems. It's, yeah, moving the segments in a way they shouldn't. Let's try again this one. Since we now fixed that other thing with the rigidity. The tension seems to be better. That redness doesn't appear so much anymore. What happens now? I think it's gonna collapse. It doesn't work. And this one seems to be very crazy as well. Yeah, no, I don't know about this. So let's revert. I should be going home. But this is so somehow. Okay, and higher gravity probably crushes it. Okay. Okay, maybe it's a little better, I don't know. This 50% value seemed decent there. Still very crazy stuff. Yeah. What if it's lower? So I want it to be close to the ground. And for some reason, it's going through the ground. Let's drop it now. Okay. Okay. Move the particles with the force. Constrain them. And then maybe we move the particles without the force. Oh boy. It doesn't look good. Yeah, no, not good, not good, not good. Okay, and what happened with this constraint? So this. Let's try also that. I don't know why they're moving like that. So here, the location is that. It don't really make a difference. Okay, but why is that here when touching the bottom? Why does it start to do those things? And can I remove this code from here? So this one, does it work if it happens? Okay. Yeah. But something then starts to happen. Yeah, I really don't know. I think this is a mistake. Let's check that source code from this other game, because that one seemed more stable. So the particles here, okay. New location, add the forces, all location. Yeah, fine. Same thing, the constraint particles. Okay, crazy stuff, bad code. Update segments. Seems kind of similar. Mhm. Okay, so looks like everything was the same. So updating this, they're not constrained there. It was done after this for some reason. But what's happening there? Where is this momentum going to, coming from? How is this momentum starting to happen there? Especially because if these particles are constrained, it's probably the tension in these sticks. Like, okay, now it was too weak there, so it collapsed. It's crazy. Oh boy. I should have given up many hours ago. Okay. So now the gravity affecting these ones is tough enough to push through that thing, and then constraining that point at the bottom is the thing that pushes the thing upwards a little bit. Now, two of these points here don't seem to do much trouble, but when the points are staying there like that, okay. Um, Okay. Was my gravity just too small? Okay. This may have done something. Okay. Crazy. So what next? I want another leg. I want another leg like this one, but flipped. So I'm very lazy right now. Um, okay, so it wants me to implement some a flip method there, but I think that we need this to be here. So true at the end of this one is flipped like so. And now generate leg. So is flipped is also going to go to this one. And generate leg here is flipped. Like that. And then here we multiply all non-zero or all values really with this one. And now it doesn't work because there's just one flipped leg. Okay, legs push flipped leg. Where is it? Oh, so generate leg is not the constructor. It's this function here that also calibrates for some reason. Now it's there. Okay. Those particles must be the same. All three of them. So 1, 0, and 2. So basically here after that is happening, 0, 1, and 2. 0, 1, and 2. Okay. The segments should also be the same. I hate this. So 0, 1, and 2. These also need to be overwritten. So sticks M, L, and A. A needs to be between particle 4 and P2 of that one. Oh no. The lengths should be the same actually, so they're mirrored. So particle 4, which is particle 2 of the first stick, needs to be... Oh, damn it. Flip leg, sticks of 0. P2 is particle 4. Okay. Now this L and M, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 11 and 12 flipped 11. P0, P1. So P1 and P2 become particle 0 and particle 1. I think. So this is 0, 1 becomes L, 0, 1. And here 0, 1, that is 0. And then P2 is 1. Okay. And then this one, M, which is 12, P1 becomes 0 and P2 becomes 2. Nope. I probably made some mistake. Oh, this is probably a bad idea. Why did I do that? So the 0th stick, this one A, the 4 is fine, but P2 needs to be 1. Why they're not attaching? They should attach. I don't get what I did here. Why isn't this 0, 1, 2? Okay, this one seems to actually be okay. Let's not move the motor. Oh no. The angle can still change. Okay, one seems to be attached fine. So the one with particle 1. Zero, 1, 2, 0, 1, 2. But then these sticks. So the first stick, A, P2 of that one, should be particles 1. Then 11, so L, zero, 1. Both of those, I think, P1 and P2. Yeah. Ah. Yeah, I also want to see the conclusion so much. It's not happening. It should be 11 and 12. I don't get it, why it doesn't work. If I attach all of them with this particles 1, what happens? crazy stuff. This one, they are attached to something. Or are they? So J and K need to be attached to 2. Oh my, I'm not looking at the correct ones. So J and K need to be attached to 2. J and K are 9 and 10. So J P1 is 2 and K P1 is also 2. Okay. And this other segment, A, has to be 1. Okay. And 0. So L, wait. No. The new one. The new stick that we had, this one here. So this last stick here has to be between 0. Yeah, which is basically 0 from the other one. Okay. This is kind of fine. But this collapses because it doesn't have any structure or something. Mm-hmm. Maybe these two far away ones can be also linked together. So I don't know which leg should I add them to, but it doesn't really matter. So 4 and 4. It adds another structure here. I guess it's kind of okay. Okay, what if the motor is moving? It doesn't seem to work because one of the motors shouldn't be moving. Yeah. I mean, the motors shouldn't somehow interfere with each other, is what I'm trying to say. Yeah, I think I will have to give up because this is becoming quite messy now. Um, the code needs to be structured in a way that you can take the pivot of some leg and based on that one generate the legs. So now I'm doing all kind of messy stuff that I thought is going to be a quick thing here, but it's not. It's becoming really elaborate. And definitely possible to do this in this way, but the code is horrible. And updating this one, move motor. Actually, what happens if we move the motor twice by passing the motor of the first leg to the motor of the second leg? Something happens. Um, yeah, very tough. And these need some offset points there. Yeah, it's much more hard than it seems. Uh, if I reattach this one point, kind of looks like it's moving. Hmm. Yeah, really crazy. Looks cool. Oh, oh yeah, guesswork at this stage. It's the only thing I can do because I just can't think anymore for a very, very long time. And this kind of trial and error stuff is the only thing that when I'm not capable anymore, I can still sort of do. But why are these points moving? They shouldn't move when they are touching the bottom. Like there should be some kind of friction limiting the movement on the X. So I want to do that somehow, but so what's the problem here? Okay. I don't want that because they're going to be forced there. But has friction is true. Otherwise, has friction is false. And with this friction, when we update, not that, but if the point has friction, it should be small. No. Why? So this velocity, okay, from the previous one. Let's try 0. I don't know why it's moving. It shouldn't move. So if the point has friction, the scalar should make this velocity vector shouldn't move. Why do you move? It's moving because of this. It's moving because of that. So the stick here in the update. Yeah. No, I am not alive. It doesn't feel like that anymore. So engine gets stuck because the things are resisting here, and I'm sticking these on the bottom for some reason. Oh yeah, that kind of stuff hasn't happened for a while. Oh wow, everything is static. Okay. Shouldn't slide. Why does it slide? So the stick updates, and this is the thing that moves them, right? What if I'm passing here these and do some messy stuff with the constraint? Like the constraint. So article here and right and bottom, like um, what did I do with the skier guy for the friction there? Is there friction anywhere? No. Crazy stuff. So if it's low enough, then the old location X is something. I don't want to go there, so and something with this stuck. Nope, not going to. Try to look at that code. Yeah. Well, it actually might help if they alternate touching the ground. It seems to be that two of them are touching at the same time. I'm not sure. I think what is happening is that we don't see during the calibration phase something, and they are getting stuck there. Okay. Okay. And what happens if this one moves again? Yeah. Yeah, now they never get unstuck. Anyway, this was kind of just as a debugging thing. Okay. So okay, it's pushing on the wall. Yeah. Yeah, I think I give up. Sorry, it's just too late. And I know what I could do, just too much work. It's funny. This. Yeah. No, this would be a horrible idea. I mean, sure, challenge competition could work, but not based on the code as it is now, because even I don't understand everything that is happening at the moment. So starting, you can take it as a basis, but only parts of it are reasonable now. Some things here should be completely redesigned, like how you create this beast from this engine. This motor is the thing that comes first, and it's only one of them. And this is passed to all the legs. That's how you should do it, but now I'm way too tired to do it. I mean, I can give it as a challenge if somebody wants to do it. Sure, no problem. Um, I'm not. I can't push to Git right now because it's a new computer and it doesn't let me. But I can drag here, uh, do this kind of upload if somebody wants to have a look. Uh, not that. And then I just give up. So it's gonna stay like this. Those who watched, I think, know kind of which are the important pieces and which are the horrible parts of the code. Um, yeah. So let's leave it like this. I don't know what to say. Maybe if somebody is able to do it, then shout out at some point or whatever. But yeah, so the code now is just like this. And in the very beginning part, you can still do the experiment, I think. If instead of generating beast, you call this one, generate legs for optimization, I think. Yeah, this seems to still work. So this was the thing with the optimization attempt. And that one is still there, working apparently. I didn't break it with the beast. So both of them can be tried out. And also this code, let's see what happens with the beast from my experiment. Oh wow, this is a different beast. It's falling because of all these structures in the middle. They are almost all straight. So really, it needs all the legs to be there, I think. And this one seems to be... It's actually walking, crawling. Is this a success? Look at it. It's going to the right. like some, I don't know. It's actually doing something. Does this count as a success? Please tell me this is a success. It's going there. Let's make it start on the left side of the screen. And something like this. And now, yeah, look at it. Going like exactly how, exactly like in the video. See? Exactly. Like there's no difference whatsoever. um, yeah, the other one didn't do that, did it? Uh, so what does this one do? It glitches out somehow. I mean, it doesn't look like it's walking in any way, but somehow this tension in these things adds up some forces. There's no friction at the bottom because I just can't think how to implement it. So then some glitch happens. But the other one, probably the same thing happens really because there's no friction there, but it happens in such a way that it kind of looks like it's moving. Like this is kind of like a leg, and then this one is pushing now that way a little bit. So it's a coincidence. It's not really walking. It's the same glitch that is happening from the previous one, but this one looks more convincing than this one that is kind of just like a magnet is there pulling it like there's no reason for it to go there, but yeah. Okay, I give up. Maybe I do some cleanup for this code also if nobody's able to do it, but I'm not gonna do it anytime soon. And I will have another live stream maybe in a couple of weeks with some other project, simpler thing this time, nothing so crazy. And if I am able to do something by then I can showcase the result. But I think that in 1 hour of fresh brain, reorganizing the code here should be okay. So something should start to happen after that. This friction and making those points not slide like that, it's probably the biggest challenge. But okay, yeah. Okay, thanks all for watching. Sorry it was extremely boring, especially in the last half, probably. I literally didn't have enough brain capacity to stop myself from this horror. So there's like this need of seeing it actually happen in practice and thinking that it's very close for it to happen, but then new things started to appear all the time and it just didn't happen this time. So yeah, but again, thanks for watching. Good luck if you try to do it. So the link is in the description there, the repository. And yeah, see you next week with the regular video, and then then maybe after that or in a few weeks, another live stream. Yeah. Okay. So how do I close this? Okay. See you.